So I want to try and keep this as, it's not a hands-on demo or anything, but as interactive as possible. So if you have any questions anywhere along the way, throw your hand up and stop me. My main goal, so the title, I changed it a little bit, it's HTTP2 in practice, but it's basically, I want to try and give you a mental model for how HTTP works from the browser through the networking stack, through the network, up into the server. So you have a really good mental model of how it's supposed to work. So you can test and see when it's working, when it's not, and when it's not working, because I can pretty much guarantee it's not, you'll understand fairly quickly how to fix it. And so if anywhere along the way you're like not entirely sure why something's the way it is or what I'm talking about, please raise your hand, ask any question. A little bit of background, if you don't know me, I built a web performance tool called Web Page Test. I also spent 8-ish years at Google working on web performance, a good time of that on Chrome. After that, I spent about a year at Cloudflare on the CDN side of things, working on web performance, HTTP2, stepping on stage lights. And then I'm at Facebook right now, also working on web performance. So I've been working on web performance since the dial-up days, just to age myself a little bit. So I've seen it all. And if you've got any questions towards the end that I haven't covered, I'm willing to give you all sorts of anecdotes from my history. I know we're being video recorded. I still don't mind going into a little bit of the sordid details on some of it, if you've got any questions. Quick tips, the second row, fifth row, and I think there's another row behind it, have power. If you want power to your laptop while we're here. I'll also try and take, I know in about an hour and a half we have a break. I'll try and take another break before that. 3 hours is an awfully long time to be sitting down, especially in these seats. So I apologize. So the general flow is I'm going to start off in the browser, probably the first third or so of the presentation. If it doesn't interest you, sorry. But it is critically important to understand how the browsers work, how they fetch things, why they fetch things the way they do for performance in particular. If none of this interests you or along the way you realize, hey, I'd rather go see this other thing, please feel free to. It won't hurt my feelings, don't need to sneak out or anything. It's your money. I want to make sure you're getting your money's worth out of your ticket here to Velocity. Hopefully I'll give you a lot of technical details and information to make it worthwhile. But if not, you won't hurt my feelings, so don't worry about it. So starting on the browser side of things. The browsers are a fairly complicated rendering engine, but at the root of it, they have effectively 3 trees that they maintain internally. There's the DOM tree, the document object model, that's pretty much what you're sort of used to thinking of if you're using JavaScript to access parts of the page. It's all of the components, the head of the document, script tags, images, all of that stuff laid out in a tree structure. So you've got like the body contains these various elements and it just sort of goes down from there. The browser builds that as it's parsing along. That's just an internal representation of what the HTML is effectively. That has absolutely nothing to do with what shows up on the screen. The browser has to take, then it also has what it calls the CSS OM or a style tree. And that's what the CSS says, hey, this is how all of the stuff should look. And what it does is it marries those two together to create the render tree, which is what actually gets drawn to the screen at the end. And so generally, it's, for me at least, it's mentally easiest to picture, okay, I have the DOM, and then the body and the rest of that part down from the DOM is what gets rendered to the screen. But it's very, very important to note that in the DOM, the only things that get rendered to the screen are within the body. So until you have a body, there's nothing to draw to the screen. And so this is like as simple as it gets for HTML, but just for a demo, I wanted to walk you through sort of what the browser sees when it's walking through a document. And so I spent way too much time working on browser parsers, but at its very basic underlying core, when you're looking at what the browser does to the HTML, there's really only a couple of basic rules. It processes the HTML as it streams in over the network. It doesn't have to wait for the whole thing to become available. So as a byte comes in on the wire, or more likely 1,500 byte packet, it'll process that 1 byte at a time. It reaches an end tag and it goes, okay, I have a token. I can process this token. So like the doc type token at the top of the HTML is a token. The HTML tag is a token. And it sort of goes through those as instructions one at a time. Style sheets, when you have an external reference, link rel equals style sheet, those block rendering because we had our 3 trees. And so the CSS OM requires the style sheets to build it. It can't create the render tree until it can merge the CSS OM and the DOM together. So you can't render anything until you've got the style sheets loaded. But they don't actually block the parser. They just block the drawing of the content. Script tags are sort of the evil beast, and that's the one that kills parsers more than anything else. By spec, by the HTML spec, when the parser reaches a script tag, if it's not an async script or a defer script, it stops until that script has loaded and is ready to be executed, and it needs to execute it before it can go on any further. That's in case the script needs to modify something that was created in the DOM before it, or it needs to create stuff that's going to be available for things to use later in the document. The other sort of tricky bit to it is the scripts may reference or try to do things that are referenced in the style sheet. So when you get to a script tag, not only does it have to wait for that script to finish loading, it has to wait for any style sheets that were referenced before it to finish loading, before it can execute that script. So script tags in sort of the parser world of building the DOM are the evil big blocker that we try and get rid of. Some really high-level browser events that you track sort of from a technical measurement. DOM content loaded is when the parser reaches the end of the HTML. It's basically, okay, whew, I finished reading all the instructions. It hasn't necessarily finished loading everything, but the parser made it through all of those script tags basically and reached the end of the HTML. The load event, that's when all of the static resources that were defined in the HTML have finished loading. So all of the images, scripts, style sheets, all of that kind of stuff. There's a good chance some stuff will happen after the onload, triggered by JavaScript, but the load event is sort of in a static page when everything the browser knows about has finished loading. Notice these are technical measurements that have absolutely nothing to do with the user experience. So they're good measurements for understanding technically how the browser is doing with your page. Has absolutely nothing to do with what the user is seeing of your content. So in our example page, browser gets the first tag, okay, not a problem, it's not blocking, we'll go on to the next one. It gets the HTML tag, it starts building the DOM, it's now got the doc type in the HTML, and now we're building the head. We have a title tag, but we don't actually have a title yet, so the text for the title is a separate element. We now have a title. Okay, the first thing the browser can do, and finally the first bit of feedback to the user, is it can put the title up in the browser tab. And it's often ignored, but that is an important piece of feedback to the user. So when you have like a slow back-end HTTP response time from the server for the base HTML, the main thing that will it'll delay everything, but that also significantly impacts when the user gets that first bit of feedback that the title is available. Closing title, okay, we have a style sheet, not blocking, so we can just keep going. We hit a script tag, but it's an async script, so we can keep going. We got a close script tag. Woo, hey, deadlock. We hit the first blocking script tag, so the browser parser needs to stop. And now it knows about nothing else. So as far as the main browser parser knows, it only knows what it has read of the HTML. It doesn't know anything else about your document. And so it stops there, waits for that script tag to finish loading, as well as the style sheet that was referenced before. Back in the days of IE6, this actually caused a fairly big problem in that if you had a whole bunch of script tags, the parser wouldn't know about any of them, and so it would load one at a time. It would reach this script tag, it would stop. It would execute the script, and then it would go on and get the next script tag and fetch it, and then execute it. And so you get a really long stair-step waterfall of content loading. And that's sort of where the preload scanners became a thing. We don't give Microsoft enough credit, IE was one of the first ones to implement a preload scanner. What it does is, even when the main parser stops, it goes ahead and peeks ahead in the rest of the HTML and goes, okay, I'm going to look through and see if there's anything else that looks like I'm going to need to load it, and it starts loading. So it goes ahead and it can see the other script tags, the image, the 2 images, and the 2 other script tags, and it can start fetching those preemptively. The main parser, we just keep going along. We hit the second script tag, it stops again. It needs to wait for that to be ready. Hopefully at that point, the preload scanner has already loaded the second script, and it won't be waiting too long. We haven't actually drawn anything to the screen yet. And so this is one of the main reasons when we're doing front-end optimization, we try and get as many of the scripts out of the head of the document as possible, because they all block anything from being drawn in the content. Now that we hit the body, we can at least draw the background of the page. So if the style sheet has a background color, we can go ahead and draw the background of the page. We see an image reference. We've processed it. We don't block or do anything with it. We go ahead and trigger a fetch and say, hey, I'm going to need an image here. Let me know when it's finished loading, and I'll draw it in its place. Hopefully, either the style sheet or on the image tag itself, you've given it dimensions. If you don't have dimensions, the browser doesn't know how big of a space to reserve, and you get all of that jank that you love when you're browsing pages, and it'll move your content around when the image loads. Header tag, second image, still not blocking. We almost made it. We hit another script tag down at the end of the document. It's less of an issue at this point because it's already loaded all of the body content. If any of those images load at this point, they'll go ahead and render while it's waiting for the script to load. So we tend to treat blocking script tags down at the end of the document less important than the ones at the top, because they don't block render. Right? They sort of block you from reaching the technical DOM content loaded. They've got some functionality that may not be hooked up yet, but they're not actually blocking the UI from drawing. Then we can finally make it to the end of the document. And at that point, the browser files DOM content loaded. Woohoo! I've actually made it to the end of the HTML. I haven't finished actually building your page. When the 2 images, the logo and the main image load, then it fires on load. And back in the good old days of HTTP 1, it would be done. Assume everyone's still with me okay? No one's asleep yet? Yes? Yes?
So by the time that loads, can we say the rendering for the welcome to HTTP 2 has completed?
So there's an image and a script tag at the end, and the question was, at that point, can we say welcome to HTTP 2 has rendered? We can say that welcome to HTTP 2 could have been rendered. Browsers are interesting beasts. They try to be as aggressive as possible in processing your content and render as few times as possible. So where I'm sort of getting with that is, if script3.js had already been loaded by the preload scanner and it was ready to run, there's a good chance the browser will run that before it yields to render, because it wants to try and avoid doing duplicate work too often. And so if every point after the body, if it did a layout, so layout calculations of the browser are fairly expensive, especially like on low-end phones. You can actually see it take seconds to sort of lay out where everything needs to be on a page. And when it has to redo a layout, sometimes it actually has to recalculate where everything goes. And so if the browser did a layout when it reached body, and that it did another layout in a paint when it reached image, and another layout in the paint when it reached H1, and another layout in the page when it reached image, it would be very, very slow. And so what it tries to do is it tries and builds as much of the DOM as possible, and then draw. And so it's in a bit of a race. And sometimes you'll end up seeing a situation where you'll improve the loading of things, and the visual experience actually gets slower because you gave the browser a chance to do more work in the time that it normally allots. And before it goes, okay, I've done enough work, let me draw something to the screen, which is a little counterintuitive and something you have to be a little careful of, especially if you're doing testing where you're testing like one connection profile in one situation. You may end up making it look slower in that one case, but actually be faster in a whole lot of other cases. But in the case where like script 3 hasn't finished loading yet and the parser stops, yes, then welcome to HTTP 2 would draw both of the images whenever they load, would draw independently of the script.
So is it blocking? Like we have H1 welcome to HTTP 2. So is it blocking before the image and script and the end?
So the H1 welcome to HTTP 2, is it blocking? No. It's a DOM node. The parser sees H1, it creates an H1 element, and it sees the text, and it adds the text to the DOM, and it sees the closing H1, and it adds that to the DOM as it's building it. And it just keeps on going, building the DOM tree. And it has a style tree. Now, when it decides to merge those two and create the render tree, that's where the browsers have their own logic. Like Chrome, for example, I'll reference Chrome a lot because I'm very familiar with it. But we have a couple of rules. If we've processed something like 2,000 tokens in a loop, we go, okay, you know, we've done a lot of work, we haven't yielded, let's yield and let any paints happen. But that does mean it'll process up to 2,000 things in your HTML at a time in one chunk without yielding or waiting, if it can keep going, right? So if there are like a whole bunch of paragraph tags and a whole bunch of H1s and H2s and even image references, it'll process like 2,000 of those without stopping. It's not doing a lot of work, it's just building a tree in memory. We have some other logic that if we hit a blocking script tag and the script is available and we've processed a certain number of DOM elements, I think it's something like 200 to 500, we will yield before running the script to let paint happen. The main use case for that is there are a lot of content sites. I think Macworld is probably the one I was looking at when I implemented it. But where they put really, really expensive scripts down at the end of the document. So like they had a script that would take 5 seconds to evaluate and run. And usually the browser would go, okay, I have that script available. I'm not blocking. I haven't processed or done more than X hundred milliseconds worth of work. I'm going to go ahead and run the script. But before it runs the script, the browser has no idea how long it's going to take to run. And so that was a sort of a trade-off to go, you know what? There's a good chance whatever script we're going to run might be expensive. Let's draw something to the screen before we run the script. And so you'll end up with a lot of magic like that the browsers do, where you can't necessarily predictively say the browser is going to draw to the screen at this point, because they do try to be as eager as possible. But until you get to blocking scripts, everything else is basically just building an in-memory tree. And so it's just processing text, building nodes, and that's theoretically really fast. Got it? Okay. Everyone else good? All righty. So, you know, it's not everything is referenced in the HTML. So we had the preload scanner that can scan ahead and sort of discover all of the other resources that are statically defined in the HTML, which works great if you've got a case where everything in your page is actually defined in the HTML. But we've got some fairly painful resources that aren't statically defined. These days, fonts is one of the big ones. Everyone seems to like custom web fonts, or 4 or 5 of them. Fonts and background images they're defined in the style sheet, and the browser doesn't know about them until it actually applies the style sheet to a DOM tree, does layout and styles, and goes, oh, hey, I need this background image for this place on the page, or I need this font for this text that I'm trying to draw. And we don't have any predictive ways to scan ahead and detect those, so they are really slow today. And I mean, if you think about it, it's at the point that the browser is trying to draw text to the screen that it discovers, oh, I need a font to draw this. And then at that point, it needs to go and fetch it before it can go ahead and apply it and draw to the screen. There are some workarounds, none of them are great. There's a font display CSS property where you can do like swap, which says, hey, use the fallback system font until you get the custom web font. Your designers may not love you for that because you get sort of that flash of drawing old text and then drawing the pretty text that they specified. It used to be the case that some browsers, I don't know if Safari still does it, some browsers would wait forever to load the font before drawing any text. Most of them these days wait up to 3 seconds by default, where they'll go, hey, you know what? I'll give it 3 seconds to load to the custom font. If it's not in by then, I'm going to draw my fallback font. So you have to be really careful with fonts in particular, but background images are also another hidden one. Script-injected content sounds painful, but it's basically if you have JavaScript that writes anything into the page, the browser has no way of knowing what your code is going to do to the page until your code actually does it. The most common use case for that is A/B testing or tag managers. So if you have Google Tag Manager, Optimizely, something like that, what they end up doing is they're a script tag that you inject usually into the top of your page. It goes out, loads their library, which goes out and loads some configuration data, which then does usually like a document.write, which is a way of injecting HTML into the page wherever the script is running. And they will insert whatever random tags someone has configured in an external system. And usually they're a way for marketing teams to add things or mess with the pages without having to go to dev teams. So it's kind of an end round around the dev process, at least on the tag manager front. And so you end up with cases where you'll have like 200 tags that were added that are all getting injected by this tag manager because at one point, a marketing manager added something to the page that they thought was going to have lift, and then they forgot about it. And so you end up with a case where you have like all sorts of cruft built up in these tag managers that aren't monitored from anywhere. And all of it is invisible to the main parser until it actually goes to execute the code. So a really easy win on the web performance front is usually to audit the tag managers and see what all's in there and make the owners for it actually justify the benefits rather than, if every A/B test and every tag manager tag brought the benefits that they were promised it would bring, you would be making like 10 times as much money as you're actually making. Import is within CSS, you can import another CSS file. And so it's a little painful to go out and load a style sheet, see an import and go, oh crap, okay, I need to load this other style sheet before I can apply the style sheet. And so that's another case where you have late discovered resources that the browser has no way to detect until it actually applies the content. As far as I know, those are the main cases. There's probably some others that I've missed. But you have to really kind of be careful. Usually, and I think I've got a bit on it towards the end, you can try and hint to the browser and say, hey, I know you can't see it in the HTML, but if you use like a link rel equals preload or prefetch, you can tell the browser, I know you're going to need these resources. You can't see them in the HTML right now. Go ahead and start to load them to try and get a head start on some of the things that you know are always going to be hidden. So now we're going to get into the actual loading. This is a slightly different version of the page. We're going to have, and now we're not going to be talking about sort of the HTML structure, but we're going to be looking at actual network fetches. And so we're going to have one HTML for the main document itself, one external style sheet, 4 scripts, 2 of which are blocking in the head, 2 of which are, I don't know if they're async or blocking at the end. They both get basically the same prioritization. One web font and 13 images, 5 of which are visible. And so inside of the browser, when it gets a whole bunch of requests, usually the requests are fed to it by the preload scanner because it can scan the entire document and go, hey, this is everything I know about. Go ahead and fetch it all. It needs to decide what order it needs to fetch things in. And so the browser has an internal prioritization tree that it keeps. As you'll see when we get to HTTP2's prioritization tree, the browser's prioritization tree is really, really simple. Chrome has 5 levels of priorities. Basically very high, high, medium, low, very low. Oddly, the Chrome renderer, which is the browser process that actually renders the UI, and the networking stack both have 5 layers with very similar names, but they're offset by 1. So depending on what you're looking at, high in The renderer is actually medium in the networking stack. And so if you're looking like at DevTools, you'll be looking at, these are the renderer versions of the prioritizations. If you're looking at like a Chrome netlog trace or the trace viewer, you'll be able to see the networking stacks version of those. It confused me more times than I care to admit when I was working on the code, so be very, very careful when you're looking at those. The offset by 1 is very confusing. But basically, HTML and style sheets get the absolute top priority because by the time the browser knows about them, they're absolutely critical for render. Below that, and this is sort of as we're going through parsing these resources, so it doesn't know about the font yet because the font's late discovered. What else does it not know about? It knows about the scripts. Oh, and it's got, the preload scanner has scanned all of the images, so all 13 images. Chrome differentiates scripts in the head versus scripts late in the body. The differentiator between late in the body is an image tag. So any scripts that are after the first image in Chrome are considered late in the body scripts. Those are given a low priority. Actually called low. The main case for that is trying to differentiate between those that are blocking rendering of the main content and those that aren't blocking the render. Using the image as the distinguishing between the beginning and the end or late body, it's mostly because we talked about how the HTML is parsed 1 byte at a time. The browser has no idea of knowing how much HTML there is while it's parsing it. And so it's sort of going down this tunnel, not knowing where late body is, where the end of the body is, right? And so it needs to know, okay, is it likely that I've drawn a bunch of content? And the sort of arbitrary placeholder we picked for that is, hey, if it's drawn an image, odds are it's drawn some content. So the scripts down at the body, end of the body are low. The 13 images, it has, at this point, it has no idea what's visible in the viewport or what's not. So all 13 images are very low priority. Chrome's got another optimization that we did that once it knows an image is visible in the viewport, it'll boost the priority to try and get the visible content loaded as quickly as possible for the user. And so when it does the layout and the paint, it's discovered it needs the font. As we talked about, when the browser knows it needs a font, it needs that font now, right? Because it's trying to draw the text. So fonts get the absolute highest priority to say, hey, I know we've already started to fetch all this stuff, but I want that font now before everything else that you already know about. And it also takes the images that are visible in the viewport and boosts their priority. Sorry, waiting a second. Okay, all good. I'll also share the slides, by the way, so you don't have to worry about taking too many notes. At the end, I've got my Twitter handle. I'll tweet it out there. I'll put it on the course entry, I guess you call it, for this on the website, on the Velocity website. And so now we've got the 5 images that are visible in the viewport. They get a high priority, not quite as important as the font, but still very, very important, and more important than the scripts down at the end of the document, and certainly more important than all of the images that are outside of the viewport that the user can't currently see. If the user does scroll at some point, it's going to pick up whatever images show up into the viewport and boost those priority as well if they haven't loaded yet. So it's worth noting that at this point, everything's in flight. So we've made it out of the head because we've done the layout. So the HTML, CSS, and blocking scripts have finished loading. So at this point, the font is the most important thing that the browser knows about that it needs to load. So prioritization in the world of HTTP 1, oh, for the simple days. The browser would maintain 6 connections per origin. An origin, as far as the browser is concerned, is the protocol, HTTP or HTTPS, plus the fully qualified domain, so www.example.com. There's sort of another flavor that also gets added to origin is whether it's a cross-origin resource or not. That mostly comes into play with fonts, but for the most part, just assume 6 connections per protocol and host name. And basically, so HTTP 1.1, as deployed by all browsers, because they don't do pipelining in the wild, is basically a fetch 1 resource at a time per connection. So I've got 6 available pools to pick from. Whatever my 6 highest priority things are is I'll fetch over those. As a new connection becomes available because something completes, I look at my prioritization tree and pick, okay, what's the next thing that needs to come be requested for that origin? It's probably worth noting, now I can't, as far as priority order, we have the 5 priorities. We also keep track of the order things came in. So at each prioritization level, it's an ordered list, basically, of when the resource was discovered. So in theory, if you've got a whole bunch of scripts that are all at the same priority level, they'll be downloaded in the order that they're discovered in the HTML. So that was the nice, simple days. When we're fetching the content that we just talked about, first thing it knows about, and the only thing it knows about, is the HTML. Chrome will eagerly open 2 connections when you navigate to whatever domain you've navigated to. So you'll have the main connection that it opens for the HTML, and then 1 extra connection that it opens because it's going to assume you're going to request something else. The browsers will only open up the 6 connections if it actually discovers you have 6 resources across those domains. So it'll open them up only as needed once you get past the main HTML. And so it discovers the CSS and sort of everything else that the preload scanner could discover. At this point, the CSS is on the 2nd connection. The browser now sees, oh, I've got a whole bunch of other stuff. Let me open up 4 more connections so I have 6 to this origin. In this very simplified case, we're also assuming everything comes from 1 domain and there are no third parties because we're in an ideal world. The 4 other connections open up. We can start downloading the 4 scripts. Only 2 of them are actually high priority. We've got 2 others that are low priority, but we're going to use up all 6 connections all at the same time anyway. HTML finishes. We start downloading the first image because we get a free resource. CSS finishes. We start downloading the second image. The 2 scripts finish. We're downloading now 4 images and 2 low priority scripts. We haven't quite done layout yet because, like I said, layout and style can take up to a second in some cases to actually calculate. So we've already started fetching stuff before we've done the layout and style. Now we've discovered, hey, we need a font, and these images are high priority. For the most part, it's fairly good. We were already downloading 4 of those images. We don't have the font yet. We don't have a connection available for the font. Whenever the next connection becomes available, one of the async low priority scripts finish. Okay, now we can start requesting the font. We can now start requesting the other high priority image, and then we'll just sort of work our way through the rest of the images as connections become available. And so it works out fairly well for the most part. Sort of your granularity of control in the HTTP 1 world is an entire resource at a time. And so that's your reaction speed to react to changing priorities is, hey, I need something really important. Whenever the next connection becomes available, I can start dealing with that. Things that are in flight, you can't do anything about. HTTP 2 prioritization completely changed the world for browsers in particular. Everything is sent to the server all at once, all over the 1 connection. The browsers will still open, or at least Chrome will still open 2 connections to the origin because it has no idea that it's talking to an HTTP2 server when it starts to open the connections. Once it has the connections open, it doesn't need to open more, but odds are even in an HTTP2 world, your servers are still going to see 2 inbound connections from Chrome for every navigation. HTTP2 has its own dependency tree. Resources are called streams in the HTTP2 world. So every image, every script, the HTML fonts or whatever, each one of those is going to be a stream that you request over the HTTP2 connection. And then beyond sort of strict dependencies of saying deliver them in this order, the HTTP2 dependency tree can be weighted. So you can say give 50% of the bandwidth to this element, 20% of the bandwidth to this one, and the remaining 30% to this subtree, which has these other elements. And you can build all sorts of really complicated tree structures in HTTP2 to try and deliver something optimally in theory anyway. And And then you can also change the prioritization. So for like the cases where we had images that were normal priority and then we boosted them because they became visible, there's a priority frame in HTTP2 where you can say, hey, I know I said this belongs at this place in the tree. Can you instead move it to this other place because I need you to download it sooner? Or in theory later, although I don't know that any browser deprioritizes anything. So in practice, what that looks like, there's a root that elements are built off of, and then you just sort of add nodes to it. Each node is a stream. And so you can have, like in the first one, A and B, they are weighted by the number that you give them. So 12 and 4, the A stream gets 3 times the bandwidth of the B stream. And it's basically the sum of all of the weights on that level, and then whatever fraction for each one of the nodes at that level is how much bandwidth they get. And if they have children nodes, like in the last case where we have D at the root, E and C at the same level, each with 8, so they get 50-50 split between them, the descendants of C, once C completes, split that 50% that C owned between A and B. So it's like A at the bottom has, 3/4 of 50% of the available bandwidth, depending on what else is downloading at the time. Incredibly powerful, incredibly confusing, which is sort of why we're having this whole talk, because no one actually gets it right. So from the browsers, actually really quickly, because it's really important that this is clear, are there any questions on sort of how the HTTP2 tree model works? It's worth noting, and I'll talk about it in a little bit when we get to Firefox, that the nodes in the tree don't actually have to necessarily be a resource. Firefox uses placeholders, so it'll create a phantom stream. Like in this case, C could be a phantom stream that's a group for resources that go under it. And so you can chain things under phantom placeholders if you want to logically group different types of resources together. Sort of more of the power. You don't have to depend on other resources specifically. So from the browser's perspective, the optimal way to load scripts would be to pipeline them. Load script 1 and then script 2 on the network instead of loading them concurrently. So in the HTTP 1.1 world, we would be loading them concurrently. We have 6 connections. We let the network sort it out. We download them at the same time. In HTTP 2, we can decide, do we make them dependent on each other? Do we put them at the same level and share bandwidth? What sort of model do we use? If you download, say, 2 megabytes of script, it's going to take the same amount of time to download 2 megabytes, no matter how you carve it up. There's only so much you can shove through the wire. What you get by pipelining them or loading them one after the other is you can be downloading script 2 while you're parsing and executing script 1. So you can be running the CPU-intensive stuff on the browser while you're doing the network activity of script 2. And so for scripts, style sheets, sort of all of your atomic content, it makes sense to download those using 100% of the bandwidth for the most part and just daisy chain them in order. On an overall page, that might look something, so this is the page that we sort of looked at in a minute. Let me see, I don't know that. Yeah, I'm not gonna be able to zoom. Hopefully you can mostly see that. The purple in the middle is the 5 visible images, and the purple at the end are the 7 not visible images. And we have sort of the HTML. The way it's visualized is left to right is time, the order sequence that we want to download things, and vertically it's how we split the bandwidth effectively. And so we want to download the HTML first, then the CSS. Because the CSS blocks being able to execute the script, we want to get the CSS before we get the scripts. And then we want to download the 2 scripts in order. At that point, we can draw the body. We can draw something on the screen. We can do the layout. And we can discover which images are visible, and we can discover the font. And at that point, we want the font as soon as possible. So we want the font immediately after that. I'm partial to progressive rendered images. Maybe it's my old dial-up days of blurry images growing sharp. But for me, at least, loading images, they're a little different in that optimally you download them all concurrently, the visible ones at least. So you can have, say, 5 images loading blurry to sharp versus an image loading entirely, then the next image loading entirely, then the next image loading entirely. The main reason for that is JPEGs, at least, if you're doing a progressive JPEG, by the time you reach 50% of the bytes, it's almost visually indistinguishable from 100% of the bytes. That extra 50% of the bytes is some sharpening, like grass blades and hair and that kind of things. And so it's almost visually indistinguishable from the end state by the time you get halfway through the downloading. Whereas if you're downloading entire images one at a time, you have to wait for an entire image to finish before you can see what the next image content is. Hopefully I'll convert you all to progressive image believers by the end. It's a very religious thing, and you'll see people on both sides. The thing is, that's not necessarily the case for all browsers. Chrome will render images progressively, so will Firefox and Edge. Safari will not. So like a progressive JPEG, for example, they will wait until it finishes loading completely before they draw any of it to the screen. That's mostly a battery trade-off that they're trying to make, is they're trying to draw the image and decode the image as few times as possible. So this is probably actually a worse model for something like Safari, where you're in a much better situation if you download an entire image one at a time, because that's the only way it draws them. And then after the 5 visible images, we have the 2 async scripts, or the scripts at the end of the body. We'll download those sequentially so we can execute them in parallel. And then, actually, before we do that, by the time we've downloaded the 5 images, the page is visually complete. The user thinks everything is done loading. There's nothing visual for them to tell that it's not. And so that we're roughly only halfway into the actual time it takes to load all of the page content, and it looks complete for them. So in this case, we're looking at like a 50% improvement in the download everything case until they think it's done, right? And then sort of towards the end, we're loading the 7 images that are all down below the viewport. Honestly, for those, I couldn't really care if they're downloaded one at a time or all concurrently. In that case, one at a time might actually make more sense, because if you have like a long newsfeed article, for example, you've got a whole bunch of story images, and the user is going to be scrolling rather than loading them all at the same time. Maybe it does make sense to load them one at a time, sort of in the order that the user would be encountering them. So it's more likely than not that by the time they scroll down, they would have loaded the images. And so visually, I'll give it a second. So in a second, the animation is going to pop up, which just shows visually what that looks like from an experience of what the browser's showing as it's loading the network content. And so we're loading the scripts now. Woohoo, we can draw something. We've got the font. We can draw the text. Now we're drawing the images, and roughly halfway through the images, it looks complete, and now it's visually complete. And so that's sort of the visual experience when you load it in an optimal case. It sort of pops really quickly. You get most of the images loaded really quickly. All of the text is there the way you wanted it. And you're not waiting until all of the content finishes. The absolute worst case, and this is Edge's model, so it's not like a theoretical. This is actually happens in the wild. We download the HTML first because there's nothing else to download. Everything else that we can discover, we download in parallel, all at the same time, sharing bandwidth among them. And since the font is late discovered, we don't see the font until we're almost done. The pain point with this, and I'm really simplistic here in that I'm assuming everything is the same size. So they all download at the same speed and they all finish at the same time. But we have the head critical blocking render resources. The CSS and the 2 scripts are sharing the bandwidth with all of the invisible content. And so we can't make it past the head because the parser is blocked waiting for those scripts to download until those have finished, and they're competing with all of the invisible content. So we don't actually have anything to draw until right at the end when everything's finished. And then we've got everything to draw, but we've stared at a blank screen for 19 seconds in this case, I'm pretty sure. Yes, I guarantee you it's still animating. And that pause and painful feeling you're feeling is the same pain the users are feeling when they're staring at a blank screen going, is it actually doing anything? And then it can pop and draw the text after it finishes loading. And so this is sort of one of the key reasons I spent years working on it, but that we spend so much time working on resource prioritization within browsers and in the web in general is that the order that you download things in makes an enormous difference to the user experience. Yes?
Very much makes defining the fonts or the style sheet on your HTML document get ahead of that.
So is there any way to get ahead of this by documenting the font in your style sheet in the HTML document? You can preload the font, which would basically load it in concurrent with everything else. But even if you defined the font in the HTML itself, it still wouldn't be able to discover it until it did style and layout. And it can't do style and layout until it's finished executing the script that are in the head. So if you have no scripts in the head and you define, and you basically have an inline style sheet in the head, then yes, it can load significantly faster because then you have nothing blocking render. That's a very rare case. It's certainly an optimization we push for. I can't remember exactly what we call it, but where critical style sheets, I think, something like that, where you inline the viewports or the style sheets needed for the viewport, including fonts or whatever else. And then down at the end of your document, you include the full style sheet so that the browser can go through, do the layout, render everything, draw content without making any external requests, and then block and load the real style sheet and redoes layout, but hopefully nothing changes as far as the user is concerned. Pulling out what that critical CSS is a little complicated. There are tools you can, Filament Group, I think is the group that has they have a critical style sheet CI pipeline tool where they can render your page in a bunch of viewports and go, okay, these are the styles that you need on this page. Go ahead and inline this content, and this is what you load at the end. But getting a head start on the font itself, the only way to do that is to preload it. We'll get into it more towards the end, but you also have to be very careful preloading. Like I said, the order you download things matters very much. And when you preload a font, you're also saying load this font maybe before some other things. And so you can get into a situation where you're preloading the font before the style sheet. So you will block all render until the font is available, which may be a good thing, may not be a good thing, depends on how tied you are to that font. But it's sometimes nice to be able to display the background content, the images, and the layout while you're waiting for the text to load. It's one of those sort of trade-offs. I've got strong feels about fonts. If you can convince your designers to use system fonts, they're awesome. But yes, a lot of web performance in general is trade-offs, and there's usually ways to do it, but you have to be careful that you're not shooting yourself in the foot as you're doing it. And so measure, test, sort of lather, rinse, repeat. Yes?
Do you have to take a guess as to why IE or Edge uses this kind of structure? Like, would that guess
So if I had to guess why IE or Edge uses this kind of structure, I've got a fairly good idea. Luckily, Edge is moving to Chromium, so it's going to be not an issue for the most part. So the way Edge is designed and IE in general before it is it's separated into two pieces, the networking stack and the browser engine. And so the browser engine actually uses the Windows APIs for the networking stack. And so there's WinHTTP and WinINet, which are sort of the low-level way of saying, fetch this request for me, fetch this request for me. And that API layer has no way of passing prioritization information. And so the Edge browser has no way of telling the HTTP2 networking stack what order it needs to get things in. It can only say, hey, these are the things I want. And then the networking stack goes, I have no idea how to prioritize it. I'll just send everything out without prioritization. It's also the reason IE11 HTTP2 support depends on what OS you're running. Luckily these days, most everyone is running at least Windows 7 or later. But if you're running IE 11 on Vista or something pre-Windows 7, it can't do HTTP 2 because the HTTP 2 stack is actually part of Windows. And so that separation is largely what limits their ability to control that. When they move to Chromium, it has the networking stack built into the engine of the browser, and so they're not tied to the OS anymore. Safari actually has a similar challenge in that on iOS and on OS X, they also have a separation of responsibility where they use core networking, which are the APIs for the networking layer for all of the HTTP2 stuff, but they do have a way to provide some prioritization information. And so I will show the different trees that the different browsers use. And that's one of the reasons that Safari has a fairly simplistic tree as well, is it doesn't have a rich interaction across that API boundary. So do I see much difference between JavaScript engines on the different platforms and what impact that has on rendering times? Yes. The actual impact is hard to predict. It's largely going to depend on what your script is doing. Safari's JS engine is blazingly fast. But their hardware is also blazingly fast, so it's kind of hard to separate the two. So like iPhones, the CPUs on the iPhones are like desktop class effectively, whereas the CPUs on Android are much lower speed. So when you're talking mobile, it's a little hard to separate the JavaScript engine from the platform it's running on. But there's definitely, yes, I guess it's the short way to put it. You're going to have to largely test and profile and see. JavaScript generally depends on what your JavaScript is doing. You want to keep an eye out for how much time it takes to parse an eval to see how much impact it is having on the rendering times. It's not unusual to see, especially test on low-end devices, on like some of the lower-end Android devices. I think the times are something on the order of 1 millisecond per kilobyte of JavaScript to just parse the text. So 1 second per megabyte is the easy math that I have. And that's uncompressed JavaScript. So don't count your gzip sizes, please. So for every 1 megabyte of JavaScript you're sending down, you can guarantee on low-end Android device it's going to take 1 second just to parse that. And it needs to parse and eval it before it can go on past that. And so that's the one case where you can sort of see, based on the size of the JavaScript, what impact is it going to have on rendering. And that's mostly if the JavaScript is in the head. If you can make the JavaScript async or put it down at the end of the body, Chrome will run JavaScript parsing on a background thread. So it may not actually block anything as far as the user is concerned, except for hooking up whatever presumably you've got that JavaScript on the page because you want it to do something. So it may take a second or whatever for that something to be hooked up, but it won't block the rendering or whatever else. And that's sort of where we get into the sort of ordering and sequencing of how we deliver things and what matters and what's critical to get loaded sooner or not. And it's one of those things where you can always wait a release and watch it get faster. And then you add more JavaScript to suck up the benefits. But V8 in particular, I know on the last Chrome 74 had some pretty massive perf improvements to parse, where they didn't used to, but they'll now parse the JavaScript as it comes down the wire. And so as you're downloading it, if it takes you a second to download the meg of JavaScript, it will be incrementally parsing it while it's downloading it, and so you don't have to wait another second after it's downloaded to execute. And so hopefully we'll continue to see little iterations on things like that. So yeah, I had to throw this in there because I spent so much time drawing it for a blog post. But this is the visualization of how HTTP2 works when we're reprioritizing resources. And it's like, you've got the one connection, you can say, hey, we've got A, B, and C coming in flight, and then X is going to be a really high priority resource. Let's see if it restarts the animation. Yeah. So you'll start out, give me A, give me B, and so we've got those, and give me C, and C starts downloading, and then we discover the font and go, oh my God, give me X now, HTTP2 can interrupt the stream because it has all of the knowledge on the server, and it doesn't have sort of this blocking connection view. And it can interrupt an in-flight request with a high priority response. And so in theory, you no longer have a one response or a one request lag time in being able to deal with prioritization changes. In an optimal case, you have a one RTT, a one round trip time between the browser and the server to say, hey, reprioritize, or I need this critical thing now. And in theory, you can get it immediately after you asked for it with the round trip to the server, interrupting whatever happened to be in flight at the time. The other thing you want to watch out for, and I get this way too often, is waterfall charts for HTTP1 and HTTP2. So in HTTP1, we're used to seeing one resource at a time on a connection. The time to first byte in particular is the place where I see confusion come up most often. Is you'll look at like an image that's laid in the document and go, okay, well, it was requested on the connection at this time. It has its own connection, so the time to first byte is how long it took the server to respond to that. It's a little naive because it's kind of ignoring everything else that's going on at the same time across all of the other connections. But for the most part, you can trust that when the browser asks for something on that connection, the server will respond immediately. And so when you have a slow first byte time in HTTP1 world, it was a problem. In HTTP2 world, the browser tells the server everything it knows about, and then the browser sends them back in whatever priority order, in theory, that you asked for. And so you could get a case where you have like an image, let's say number 10. Well, this is a bad case because that's CSS, which should have been downloaded soon. But you've got like a 1.6 second time to first byte. And it might be a problem. If that was HTTP1, that would be a problem. You'd be like freaking out, yelling at your CDN vendor or whatever. But in the case of HTTP2, you have to look, okay, what else is going on that connection? What other high priority resources is the browser asking for? And you may end up just having a case where you've got a whole bunch of scripts and style sheets that came before it that are downloading on that connection, and the server just hasn't responded with the resource you asked for yet. And so when you're looking at an HTTP2 waterfall, it's a lot more complicated because you actually expect to see everything requested right at the front, and then your stair-step waterfall happens in the resource downloading, rather than the normal stair-step where you get, I guess this way actually, where you delay the request and then you expect to see a response immediately. And so probably the number one question I get is when people first switch on HTTP2, they think everything's broken and they think their server's not working because they see slow responses, and that's normal. Unfortunately, you have to sort of look at the whole waterfall at this point. You can't look at an individual request anymore. So we talked a little bit about how the different browsers have different models. So Chrome implements a linear list. Everything is chained after one another in the HTTP2 tree. And it's all done based on the prioritization. So we have the very high, then high, very high, high, normal, or medium actually, low and lowest. And so they're chained in that order, and then within any group, they're basically in the order that they were discovered. And so when a new resource is discovered, let's say the font at a very high priority needs to be injected into the tree, Chrome rebuilds the tree and basically sends a priority frame that introduces this to the top of the list. It's not much of a tree because it's a straight down tree. It introduces it to the top of the list. It sets exclusive flags on everything, which is the HTTP2 way of saying this one has no peers, rearrange everything to follow it. And so it basically injects everything after the last resource with the same priority level that's currently in the tree. And so in this case, if it had another normal priority resource, it would inject it right after the last normal priority resource and before the first low priority resource. And so Chrome basically builds a really long list to download everything in a blocking order, one after the other. When we talked about the optimal loading case, that's actually fairly close. In my opinion, it falls apart in the case of images. We never got around to trying to fix that. And it's one of those things where once you start introducing parallelism, your HTTP2 tree becomes a lot more complicated, whereas building just a linear list is fairly easy. as far as HTTP2 is concerned. And so it works well in just about all cases. Firefox uses placeholders. So when you first open an HTTP2 connection, they will fire off 5 streams immediately, no matter how many requests you've got. And those are the placeholders for the different groups they have. And they basically have them set up so that we've got leaders, background, blocked, and they weight them so on the edges of the graph are the weights for each one of the groups. So the leaders get a weight of 201, unblocked get 101, and background get 1. And what effectively that does at a group level, 2/3 of the bandwidth goes to leaders, 1/3 of the bandwidth goes to unblocked. And if neither one of those groups have anything going on, the background will effectively get 100% of the bandwidth. And that's a way of, so the background and speculative are effectively idle groups that go, anything in these groups only download if nothing else is happening. But then it splits bandwidth 2/3, 1/3 between leaders and unblocked. And then the 2/3 for leaders is split. It has a whole bunch of resources. Basically all of the blocking style sheets and scripts in the head are directly children of leaders, but they're all peers of each other. So all of the scripts in the head share bandwidth across evenly between themselves. So we don't have the sort of optimal script loading where you load one after the other. They all share bandwidth. And then there's followers, which get a weight of 1, which basically means after all of the leaders have completed, use my 2/3 of group bandwidth to download the followers, 100% of the bandwidth, 100% of the 2/3, but only after all of the leaders have finished. And that's the images for the most part. And so that's sort of a complicated way of saying, load all of the style sheets and scripts concurrently. When those are done, load all of the images. And then there's, if there are any fetches, XHRs, JavaScript-based fetches, those will use up to 1/3 of the bandwidth. So it's a fairly complicated tree. It's kind of cool and elegant in its own way, but it doesn't do anything optimally. It's really good for the images, for example. It downloads them concurrently, but your JavaScript and everything else is all just kind of throw it into the sink, let it sort itself out, and we'll run it whenever it comes down. Safari has the same 5 priority levels that Chrome has. It's actually came from WebKit, which is where Chrome forked from. What Safari does is it maps each one of those priority levels to a weight. And so the top level priority gets a weight of 256. The lowest priority level gets a weight of 8. And so everything in Safari downloads concurrently, but it gives a lot more bandwidth to the higher priority resources. So again, not great. You've got your images downloading at the same time as your JS and CSS, and the JS and CSS are all downloading at the same time. But at least the critical resources are getting more of the bandwidth than the lower priority resources. But you have kind of a smearing effect where you're delaying everything to some extent. But it is really easy to implement. And Edge, yeah, it just kind of, it doesn't try. It doesn't send any prioritization information at all. And the HTTP2 default priority model is, if no prioritization is specified, everything is attached to the root, and it gets a weight of 16. So everything gets the same weight, everything's attached to the root, so everything shares bandwidth evenly. It's effectively the same as if you opened, let's say you have 200 resources on your page, all coming from the same origin. It's as if you opened up 200 connections all at the same time and downloaded your resources over 200 parallel connections. It'll make it there eventually, it won't be fast. And so visually, this is what the differences look like. So Optimal and Chrome load pretty quick. Firefox isn't too far behind, and Safari is a little further behind it. And Edge, we stare at blank for a really, really long time. It's not quite like this in practice. This is sort of the idealized case that makes it very easy to visualize, but the effect ends up being the same. In web page test, And in Chrome DevTools, you can get the priority information. So web page test also exposes the HTTP2 information. You can see the stream IDs for each request, what connection it was on, what the weight was, and whether or not the exclusive flag was set. The most important thing probably when you're looking at them is like if you're looking at a script and you can tell fairly quickly, did Chrome think this was a critical script or not, just by looking at what the priority is. Was it a very low or medium? Medium tends to mean Chrome thought it was a blocking script. Very low, Chrome thought it was an async script, and it's kind of loading it on idle. Down at the bottom of the waterfalls in web page test, there's also a link where you can see the actual dependency tree that the browser requested. It's a snapshot in time, so it's not the actual HTTP2 dependency tree is a living thing as the page loads. And so you've got resources injecting above other resources. So in reality, while Chrome does a linear list, in this case, the four other images up at the top were actually injected at the top of the tree, just at various different points in the loading sequence. And this is, like I said, a very simple case. Usually the tree will involve a lot of scrolling to the side because no one downloads everything from one origin. There are third parties everywhere. So prioritizing across connections. This is Mad Max Thunderdome for any fans. It's basically a free-for-all. So really quick before I get into that, everyone good on sort of HTTP2 trees, resource loading, and why it matters? All right, so when we get into, whoops. Wow, I really jumped ahead. So prioritizing across connections, it basically comes down to a throw it all on the network and let the network sort it out, right? You're opening up a whole bunch of connections to servers. It may be the same server if we're talking HTTP 1.1, or in the HTTP2 case, unless you're Facebook or Google and you've got all of your content downloading from one origin, odds are you've got multiple origins that you're downloading from. HTTP2 can only prioritize resources within the one connection that it knows about. Once you cross multiple connections, each connection prioritizes independently. Across both connections, there is no prioritization. The network sorts it out. And we'll sort of get into why that's kind of a pain. You may do it to yourself as well, sort of in the old school of HTTP 1.1. It used to make a lot of sense to have static domains, sharded domains, so you can serve your images from static.mycompany.com or whatever, or you'll serve images from 3 different domains so you can get more than 6 connections open at the same time. One of the problems when you do that too widely, even in the HTTP 1.1 case, is you can get into a situation where your congestion packet loss becomes a problem and the servers start sending retransmits for data that isn't actually lost, and so you can sort of bury yourself by having too many connections open at the same time. We call them spurious retransmits. And so you end up wasting a lot of bandwidth because things take too long to transfer when you have that many open at the same time. Server assumes the packet was lost. It's really buffered. Server retransmits the packet. Both packets are now on the wire, and you end up sort of cascade killing yourself, sucking up most of your bandwidth just retransmitting data that wasn't actually lost. And so as much as possible, if you can collapse things down into one connection per origin, third parties, it's unavoidable, unfortunately. I wish we could get rid of all of them. But you can't serve third-party content from your origin. You have to be aware that you can't do a whole lot of prioritization across the two, though. They will mostly download concurrently, and they're going to compete with each other. Yeah, so in a waterfall, so web page test also has a connection view where you can see below sort of your normal one resource at a time, you can see per origin for each connection what activity was going on. And you can see what happens when you have multiple connections. So in web page test, the dark part of the bar in the waterfall is when it's actually downloading resources. The light part is when it's waiting on a round trip or that connection's idle for some reason. And so when you have a whole bunch of different connections open, you end up with competition, like in the second case, read our fonts, and we've got fonts interleaving with scripts, scripts later, fonts interleaving with images. You don't have a lot of control over what's going on. And bandwidth isn't free, so just because you're downloading things concurrently, if you're not using a tool that actually shows you the data chunks, you end up in a situation where you just have a large bar and you don't really get a sense of how much they're stealing bandwidth from each other or what impact they're having. The other thing to sort of pay attention to, we generally used to think of connections as being free. So the 6 concurrent connections or the predictive connections that the browser would set up, we wouldn't care about them too much because there's not a lot of overhead, at least on the client side. Server is a different problem, but in setting up 6 connections, because we don't transmit a lot of data. In the case of HTTPS, that's not really the case anymore. Each one of those connections also does the certificates. It's not unusual for certificates to be 15K, give or take. You start opening up 10 different connections to third parties, and you've got 150K in just certificate data that you're negotiating back and forth. That's also competing with like your HTML or your critical resources. So you have to be really careful, not just with the number of third parties you're pulling in, but what you pre-connect. So one of the hints that you can give the browser to say, hey, I'm going to need a connection to this domain at some point. Go ahead and start setting up the connection now is link rel equals pre-connect. But those aren't free in HTTPS. You've got the 16K or 15K-ish of certificates that are going to be competing with your core resources. Is everyone still awake? Do you need to stretch for a minute? We've got about 20 minutes before the official break. Probably, I'd say run about 10 minutes. If you can power through about 10 more minutes, and then we'll take an early official break so you can be the first ones out to get the snacks. So in HTTP 2, there's connection coalescing, which even if you've got static domains like images.mycompany.com or whatever, if the domain resolves to the same IP address and you have the same certificate, if your certificate contains both domains within it, then the browser is going to do the DNS lookup and it'll go, hey, this resolves to an IP that I already have a connection for, and the domain name is one that was included in the certificate that I already got. I can reuse that connection. And so in the HTTP 2 world, you can, in theory, collapse all of your sharded domains into a single connection, even without having to change any of the domains. And so you can still load from all of the different domains, but serve them all from one connection where you can prioritize. That does require that you have stable DNS, so that the IP addresses for the different domains come back and have the same addresses, at least overlapping addresses. Actually, it needs to be the same addresses in Chrome case. In Firefox, if they have any overlapping addresses, it'll consider them the same. The pain point is you still have to pay the DNS lookup cost. And so if you've got an images static domain, it still needs to at least do a DNS lookup to discover that it's the same IP. And so if you can at all, serving everything from the actual origin domain is by far the fastest way to do it. It's also the less risky. But if you have to, you can do it. In theory, there are additions coming to the HTTP2 spec for origin frames and certificate frames where the server can send down to the browser and say, hey, I am also images.example.com. You don't have to do a DNS lookup. There's some security concerns around doing that, so I wouldn't hold my breath on either one of those happening. Does anyone here do a multi-CDN deployment? Sodexis, load balancing across CDNs? Excellent, you don't have to worry about that. One of the things that does happen fairly often is, so Sodexis, there's a few other companies that'll do it. They're a DNS-based resolver that will load balance your traffic across multiple CDNs for different reasons, like this CDN works best in this region, or I've reached my build threshold for the expensive CDN, let's start using the cheaper CDN now, or different times of day and things like that. When you're using something like a multi-CDN product that's DNS-based, you have to be really careful because we talked about IP stability in your DNS. If they resolve the two different domains to two different CDNs, you're no longer going to be able to coalesce those connections. And so if you end up using a multi-CDN solution, you have to work with the provider to make sure that the maps that they use are stable across all of the different domains. And one way that we've seen them do that before is you can do it like by region. So all of the DNS requests in from one region always resolve to the same CDN. And so you can get stable IPs that way. Just something to be careful of. Trying to think. Yeah, we'll start diving in. So for the rest of the talk, we're out of browser land. Any questions on browsers? And largely in HTTP2, we're going to start diving down into TCP now. So everyone feel good? I'll get into the high-level overview, and then we'll go into the break. But so for the most part, the things that you need to care about are the two things on either end of the connection. There's the browser and what the browser is talking to. What the browser is talking to in your environment may be a CDN, maybe a load balancer, maybe a security device, maybe a layer 3 load balancer or layer 4 load balancer that terminates TCP, and then you've got something further upstream that terminates HTTP2. In that case, you need to care about both of those. But for the most part, you want to look at the outermost edge of your infrastructure that talks to the browser. I and you mostly don't care about what your servers are doing if they're behind a load balancer. The critical things for what we're going to be talking about here are the thing that talks to the browser. Yeah, and so if you've got a layer 4 load balancer, it's both the load balancer and the thing behind the load balancer that are going to matter. And if you've got a CDN, it's the CDN that you're using. And luckily, well, it's not necessarily your problem to fix, it's your problem to harass the CDN company to fix and to be able to tell if it's broken or when it's fixed. Your edges, whether that be the CDN or the load balancer, and the upstream servers that it talks to, your actual application servers, your static content servers, whatever else, those generally open multiple connections, and it's best effort. So HTTP2, the prioritization scheme, like let's say we said, we want these 3 scripts in this order, followed by this other image. If the edge server has any data available at all for any resources, it then looks and sees, okay, what's the highest priority thing that I need to send data for? But it will send data for that low priority image first, if that's what comes back first from your upstreams. So like if your edge load balancer has a bunch of caches behind it and an application server. Now say the application server is slow, but the edge caches are really fast because they just have to do a disk lookup. Even if the resource coming back from the application server is the absolute highest priority resource, the things that are served out of cache are going to be sent first because it sees them first. And that's to avoid head-of-line blocking, to make sure that you're not wasting bandwidth. It's like, of all of the data I have available, send them in this order preferred, but send whatever you have. And that's sort of critical to everything else we're going to be talking about. I think I'll probably, I'll pause it right there. Were there any questions on that? If you don't want to ask questions in the group, we've got a nice, we'll call it 40 minutes until 3:30. Feel free to ping me directly. Chat amongst yourselves, jockey for position, see if they've set up the snacks yet. All right, we'll meet back here in about 40 minutes, and we're going to talk actual reality for the CDNs, TCP, and why it breaks. So the fun stuff, for me anyway, I like the low-level networking details. All right, thanks everyone. We've sort of looked up until this point at sort of what the ideal situation is, in theory, how HTTP2 works, which is pretty much how it was designed in committee on paper. And in the case of like Speedy with Google, where everything was served over one connection, and so it can prioritize things cleanly because it only had one connection in experiments. And so we get it out of working group into the real world with real production traffic and real deployments. And it turns out HTTP2 isn't actually working as well as we might hope. And unfortunately, no one's like freaking out about it yet. So hopefully I can get you all to freak out and like start an army of freaking out and we can get it fixed. But we're not going to see the performance gains until it's actually working sort of the way we've been talking about up until now. And so for me, what triggered this off is I joined Cloudflare like a year ago, give or take. And one of the first things I wanted to do was make a bunch of our sites faster. And Google Fonts, you sort of know how I feel about fonts already. I have an extra special place in my heart for Google Fonts. It's used in like 65% of the web, which is just insane as far as penetration goes. But Google Fonts in particular requires an external fetch to a third-party domain for a CSS file for the fonts. So you need to do the 3 round trips for DNS, Socket Connect, TLS negotiation with the Google server to fetch the CSS that's all blocking your render. And then from yet another Google domain, it needs to fetch the font file. So another 4 round trips to fetch the font file after layout's done. And so to load a Google font, you're looking at 8 round trips delay to your page load for the most part. And so one of the first things I wanted to do was fix that for all of the Cloudflare customers. And so what I ended up doing was take the Google font CSS when we see it in an HTML that's being served through us, fetch it on the back end, inline it, because it's tiny. It's just like a couple of CSS rules. And so that gets rid of entirely the 4 round trips for fetching the CSS for Google Fonts. And then the actual font files themselves, instead of serving them from Google's domain, serve them from the same domain as your page, and just proxy them out to Google and cache them and everything else. And so it comes down to a 1 round trip to fetch fonts, Google Fonts, origin served when they were through Cloudflare. I was like, oh, really excited. Yes, I'll save all of these round trips. Things will be incredibly fast. And then this is what happened when I rolled it out to production. My page got insanely slow. And if you'll notice, the waterfall doesn't look terribly waterfall-y. Everything's kind of out of order. The fonts, which are the red lines, like up at the top and down at the bottom, are way delayed. The start render time, instead of getting faster because we got rid of the Google style sheet, got slower. It's like not rendering anything until I get to the end of the page. And this was with Chrome, and Firefox, which are sort of the optimal in the HTTP2 loading case. And so when it was actually fixed, and we'll get into what was actually broken, how to detect it, and all that kind of stuff, things were much better. It was rendering in a second, which is kind of what I had hoped going into it. Unfortunately, the path from this to that was like 3 months of hell in trying to figure out what was broken. So I'm trying to save you all the 3 months of hell that I went through. It ended up that Cloudflare's edge servers were not prioritizing. We'll get into why, but it was basically returning resources FIFO. The first resource that it got from its back end, whatever it was talking to, is the first thing that went down to the browser. And whatever order it got responses in from the upstream is what the browser got, independent of what the browser asked for. And so you get all sorts of random waterfalls delivering things in random orders. Not too long after that, if you guys don't know, Zach Leatherman, Filament Group, he's like font god, does all sorts of really cool things with fonts and styles on the web. This was like, I thought it was a Cloudflare only problem, and then like a month or 2 later, he tweets this out and said, hey, yeah, I moved my fonts off of my origin into a third party to make things faster. And I was like, I know what that problem is, I just saw that. And so I tweeted him and said, hey, maybe it's not your content problem or the browser problem. Check your hosting provider to make sure they're doing HTTP2 correctly. And that was sort of the start of a cascade going where, oh crap, maybe it's not just Cloudflare. So I worked with Andy Davies, who's a web performance consultant in the UK, mostly because I was at Cloudflare and I didn't want to sort of start a project that pointed out how many CDNs were broken if I happened to work at a CDN that was recently broken. So I wanted it to be semi-independent, work with some independent people to do the testing, and see sort of what the situation was. And we created a test page that specifically leverages Chrome's prioritization. And so we talked about how Chrome loads things blocking sequentially in order, and it prioritizes visible images much above hidden images. And so for testing it, it's largely the test page that we put in. It's on webpagetest.org/http2 priorities. And then you pass it an arbitrary image off of your server. And so what this page does is it will test your server or your serving that's serving whatever that image is to see how well it's doing HTTP2 prioritization. And like I said, it's targeted for use with Chrome. If you test it on Firefox, you're not going to get valid results because it's leveraging Chrome's prioritization. And on web page test, at least, you need to test it with a 3G fast connection. Chrome keeps changing. It's like every 6 weeks, it's a new ball game, and trying to keep ahead of it. But if Chrome detects a slow enough connection, and in this case, a 3G connection with like 300 millisecond RTT, it puts in its own throttling, and it will never issue more than 10 concurrent requests across the network, no matter how many connections or whatever else you have, to avoid contention. So even if you have an HTTP2 connection with 100 images on it, if you have a slow enough connection, Chrome will only request 10 at a time. And so that kind of defeats the purpose of my test. So if you test with anything slower than a 3G fast connection, you're also going to end up with invalid results. Although our first rounds of tests were with 3G because that was before Chrome changed things. And so what it does is first it'll load the image twice. It adds a query param with a unique ID just to make sure it busts the browser cache. So it loads it twice from the server sequentially to warm up the connection, establish the connection, get everything going, get TCP slow start warmed up. Then it requests 30 images, all low priority below the fold, to give HTTP2 lots of data to fill the pipe with. And then what it does is it waits until 2 of those images fill downloading, so we know that data is actually flowing over the connection and buffers are full. And then it will request 2 in-viewport high priority images, one after the other. And so what you want to see is something like this waterfall, where you've got all of the images sort of downloading one after the other, and then the 2 high priority images come at the end, and they get delivered quickly, relatively quickly, not quite as fast as they could, but still they don't get queued up behind everything else. And that's a sign that the protocols and everything else is working. The browser asked for something late that was a really high priority, and it got it delivered quickly, which is pretty much all you can ask for from HTTP2. You'll see slight gaps in the waterfall above. That's where the high priority resource interrupts the data stream of the low priority delivery, and then it goes back to what it was doing before. And so in an optimal world, your time to interrupt the data stream and send the high priority resource would be 1 round trip. The browser would have all of the data, there would be all of the data in flight to the browser. The browser would make the high priority request. The response would be injected into the in-flight data stream immediately and come in as soon as that round trip completes. And so if you look at the top of the waterfall when we're doing the warm-up, that's sort of your optimal condition. Best case would be downloading it in like 700 milliseconds or 800 milliseconds. Realistically, there's a little more buffering that goes on in that. You'll never see it, I've never seen it at least, actually be able to deliver high priority resources in flight that quickly. But that's sort of the lower bound. The closer you can get to that, the better you are. So this will be sort of a rogues gallery of how it goes wrong and when it goes wrong, what it looks like. And so the most common case is you will see it get delayed behind all of the low priority requests. And so the first high priority request basically doesn't download until all of the low priority requests have completed. And then the second high priority request, it's really quick because there's nothing else going on after that. This was a fun one. Hard to tell exactly what the server was thinking. Odds are the server doesn't support prioritization at all, and it's just interleaving data across all of the streams. And so you sort of see it doing round robin data chunks across all of the different requests all concurrently. And this is definitely one of those cases where having the data transfer chunk in the waterfall helps you see what the server's doing as it's delivering the streams. Yeah, this one, I really had no idea. It looks like it started out doing round robin for like the first 8 requests or something, and then it just gave up, and it sort of did, okay, now I'll serialize things for the rest of them. But if you look down at the bottom, the first 2 images took like forever to complete, but once they finally did, the first high priority image still got queued up behind all of the low priority images, and then the second high priority image. So the common theme is basically look at the last 2, and if they don't complete really early in the waterfall, something's broken. The what's broken is where things get interesting by looking at the waterfall, trying to figure out what the server was doing and what's going on with the network. Yeah, it looks like it's trying to do things sequentially, but it downloads like half of the image, and then it moves on to the next image and goes through all of them, and then it goes back to the beginning. So like round robin, half of the image data each time, hard to say. But same end result is the high priority stuff did not, it completed a little before. It looks like it finally decided, hey, I've got some high priority stuff, let me stop the second half of the data transfer. Not entirely sure. Yeah, and basically, this is one of those cases where the first high priority request, it didn't get delayed behind everything, but it didn't get delivered terribly quickly. By the time you have both of them, yes?
Can you just reiterate what we're looking at exactly? Like, are these tests of CDN providers with that?
So these are tests. So that
Like, what's the host being tested?
the host being tested is, we'll get to what things look like in reality, but yes, these are all different CDNs. So each one of these is how a different CDN is serving the same prioritization scheme for the one test image that's being served by that CDN. And what to look for when you test your deployment to make sure that it's working is you want to see that, not one of these. And what each one of these indicate, so this one I know exactly what's going wrong, and that's what a lot of the rest of the talk is. This one, the server software doesn't support prioritization at all, so need to rotate whatever's terminating HTTP2 to something that does support prioritization. These 2, I've got some thoughts, and we'll get to it when I talk a little bit about Nginx. Nginx is broken in its own special way that probably exposes some of these things. I have no idea, because it looks like it was doing a fairly good job, and then it just sort of lost its mind. But at the end result is the prioritization just didn't work the way you wanted it, or at least the way the browser requested it to happen. And in this case, so this is a little bit of an interesting case. This is Cloudflare. So it doesn't look as clean as the first waterfall we saw. That's intentional in an unfortunate way, in that maybe a month ago, we launched support for doing server-side prioritization, where we implement our own prioritization logic independent of what the browser requests. And so we try and implement the optimal scheme across all browsers. And so what we have here is we've got, we'll download images concurrently, up to 6 at a time, to try and get the visual experience of concurrent image loading, something more like the optimal rather than staging the images one after the other. But it does still have the 2 high priority requests still respond really quickly. It's just, at least with Cloudflare, you won't necessarily see the same stair step if you're looking at images, for example. So if you go to ishttp2fastyet.com, we're keeping a live track of all of the CDNs that we know of that we've been able to test. I'll have the results in a second here, but basically the answer is no. Only 9 of the 25 CDNs pass. the test. And just for a reality check, this is their entire purpose for being, right? Their entire operation is to serve content optimally to support the protocols and to deliver things quickly. And 9 of the 25 CDNs are actually doing it. So if you're not using a CDN, the odds of your own deployment being correct are probably less than 50-50 would be my guess. So of the CDNs, these are the only largish CDNs that actually do it correctly. Akamai, Fastly, Cloudflare, CDN Sun, I believe, is mostly a Chinese CDN. If you're using one of these, you're generally in pretty good shape, and you don't have to worry too much. If you're using any of these, it's broken in horrible, horrible ways. Big names, CloudFront, anything Amazon is pretty much broken, which is kind of bizarre because they're really big on performance. But I mean, lots of the big name CDNs, Level 3, Limelight, Edgecast, names we're used to seeing sort of all over the place. Clouds. Every one of the clouds I've tested is broken, including Google's, which is just embarrassing since they largely created HTTP2 with Speedy. And in talking to the Google teams, it's mostly some of the features that you have to turn on to get prioritization to work correctly. When they turned it on, it used a little bit more memory. They didn't see any performance impacts, so they didn't turn it on. And that's largely because they didn't see any performance benefits for search, which isn't a normal web page. There's not a lot of prioritization going on with search. Everything's JavaScript delivered. But unfortunately, if you're on Google Cloud behind a load balancer, you're behind the same front ends. And so you're subject to that. And so this is where I plead with you. If you are a customer of any of these or any of these, talk to your reps, point them to the site, say it's broken, please fix it. The painful one for me in particular, Netlify. Lots of developers love it. It's basically a static content server, integrates really easily with GitHub, for example. You can just publish, run a build of something, and it publishes it, and they run a CDN for you. And so like Zach Leatherman's test page, for example, was on Netlify, and they don't do prioritization at all, and things get delivered completely out of order. So a lot of the newer Jamstack hotness, if you would, is all broken as well. When you're doing testing for a lot of this kind of thing, it ends up being protocol level problems, TCP layer, HTTP2 layer, sort of low level. And it usually works best if you can use a slow connection so you can sort of see the effect of things happening rather than your giggy connection on your office network or whatever. In those cases, please use a packet level traffic shaper. Lots of Macs in here. Network link conditioner is built in, comes with, you have to download it from Xcode. It's basically dummy net for a Mac. Windows, there's a tool called WinShaper that I wrote basically to try and bring the same dummy net capabilities to Windows. Web page test does packet level traffic shaping. Basically something that works down at the IP or lower layer so that you can actually leverage or exercise the buffering and everything else that we're about to talk to. In particular, do not use Chrome's built-in traffic shaping. It is horribly, horribly broken for so many reasons that it will lie to you and make you think things are different than they actually are. So the reason for that, the spaghetti is the internet. It's a mess. So Chrome's architecture has multiple renderer processes, which is the sandbox where the websites load in. And it's a security sandbox, runs in a completely separate process. The browser process is shared across all of them and has sort of the safe allowed to do I/O code, and that's where the networking happens within Chrome. And so all of the different renderers talk to the one browser process, which ends up is what talks over the internet to your server. The built-in Chrome traffic shaper sits between the renderer process and the browser process, not at the network layer. And it basically throttles the speed that data comes back from the browser process to the renderer. Things on the wire happen at wire speed. So you request 20 different things from the browser process. Those 20 things go up to your server and are returned at giggy speeds. And then between the renderer and the browser process, it figures out, okay, how do we then trickle that data down into the renderer at a 3G speed, which has absolutely nothing to do with how your server would have delivered it to the browser over a 3G speed. And it gets it horribly wrong in so many different ways. And so a packet level shaper at least runs at the network layer, and it does look like, but it sits between the browser and your server, and it does actually make the connection look like it is that taking that much longer and has that packet rate basically. So on the left is what the DevTools waterfall looks like for the same Cloudflare page that's on the right. As best as I can tell, and I haven't looked at the code terribly closely, it basically round robins across all of the requests that it has data for, and basically just trickles the data in from the browser. So it requests all 30 low priority images. They come back almost instantly from the server. Then they get trickled to the renderer round robin across all of them. And then they get the extra 2 high priority requests. They aren't even made until like really late in the waterfall, which doesn't look like any of even the broken waterfalls that we had earlier. And looks absolutely nothing like the actual stair step that you get when you do the traffic shaping at the network layer. So if your devs are using tools that are within DevTools, just discourage them as much as possible. It's helpful in that it gives you direction that if you have a 5 megabyte site, it will make it look slower to you. It just won't actually make things look slower correctly. Things won't get delivered in the right order, and pretty much everything we've talked about up until now is why order matters so much and why developers need to control for order. And the fact that DevTools lies about that is doing more of a disservice than a service. The other thing to watch out for in waterfalls is some servers will give you a really thin line right at the beginning of the waterfall, which is where the headers come back for a request. So a lot of servers will try to respond with the headers immediately, and then it'll respond with the actual data for the response in whatever priority order that they were requested in. That can be useful in a couple of different cases. So in a case where you're looking at like the Chrome DevTools waterfalls on the left, where it doesn't show you the chunks of data, you'll end up with a really long dark bar because you started it when you got the headers and it encompasses the actual data delivery. But the other thing it gives you insight is to, if you are talking to a server that does respond with headers early, is how soon the server knew about the response that it was sending you and that it delayed it because of prioritization. And so when we get into like some of the Nginx cases, for example, we can see that Nginx sees the response really soon, and then sometimes it ends up delaying the response of the actual data, even though it's not supposed to. And you can sort of use that line of when you got the response headers as a, no, I know the server knew about it now, and it could get the data down to the browser. That means whatever problems are going on are within the server, not in the network between the browser and the server. So if you're using a monitoring service, Catchpoint, Pingdom, GTmetrix, Speed Curve, that kind of stuff, and they're doing traffic shaping, this is where we get back to the DevTools problem. Understand what traffic shaping they're using. Is it packet level? If you're using DevTools, Lighthouse, Puppeteer, and using the traffic shaping profiles from those directly, those end up using the DevTools traffic shaping, which, as we just talked about, is completely broken. So you generally, if you're doing your own, like rolling your own Puppeteer, you want to use, if you're like on Linux, use NetM and TC to do traffic shaping independently of the actual Puppeteer scripts. If you're on a Mac, you can use network link conditioner, that kind of thing. But do not use the built-in traffic shaping within Puppeteer or Lighthouse. It's broken, and yes, I know. Some of you are using Puppeteer and freaking out right about now. Yes?
So do you know which one of these Catchpoint
Catch point is usually running on actual connections, so they are in really good shape, as far as I know. And SpeedCurve uses web page test under the covers, so I know that they're using packet level traffic shaping. Those are the only two that I'm aware of that do realistic network conditions for testing. The other one to watch out for is if they're using like a traffic shaping proxy or something, because a proxy completely changes the network characteristics for how the browser's talking to the server and where the connections are getting terminated. So for example, this is like a GT metrics waterfall of the same test page. And so it looks nothing like any of the others, right? Except it looks a little like the DevTools one, where everything downloads all at the same time. And then the low priority stuff gets downloaded, or the high priority stuff gets downloaded towards the end. So now, everyone okay with testing? Because we're about to get into the theory and the details and protocol level stuff of why those waterfalls are broken. All right, so TCP. Basically, a whole bunch of packets, up to 1,500 bytes, give or take. There's some headers in there, so it's probably closer to 1460 bytes. Chunks of responses one at a time. These are all sort of, we'll call these packet numbers. And so we were delivering packets 1 through 8. And on the left, we have the client's receive buffer, where they receive the packets. In the middle, we have the network, the data that's in flight. The server's already sent it. The browser, the client hasn't gotten it yet. And then on the right, we have the server send buffers. And so the client needs to be able to reorder packets that might be out of order. So it needs to be able to hold whatever amount of data needs to be in flight at a time in case, like in this case, packet 1 got lost. And it needs to hold on to packets 2, 3, and 4 until the retransmit of 1 can come in to guarantee the order of delivery to the applications. And all of that buffering on the receive side is done inside of the application's TCP receive buffer. So you're dependent on how big the browser, in this case, has their receive window for how many packets can be in flight at a time as far as the browser is concerned. Well, the network can absorb whatever the network can absorb. And then on the server side, the server needs to maintain, and this is in the server's application's TCP send buffer, it needs to hold on to all of the packets that it's transmitted that the client hasn't acknowledged receiving yet, in case it needs to retransmit, like packet number 1. The client never said it got packet number 1. The server can't discard it until it actually gets acknowledgement that it's been received in case it needs to retransmit it. And so you're also limited how much data can be in flight at any point in time by how big the server's send buffer is. And each one of those, like the OS doesn't maintain its own buffers. These are buffers that the application sets on a per connection basis between the two. And so generally that's the TCP receive buffer, the TCP send buffer. And the middle one, how much the network needs to operate at full bandwidth is the BDP, bandwidth delay product. We'll get into that in a second. There's also the congestion window, which is sort of how much the network can absorb, which we'll also get into. And so the bandwidth delay protocol, let's say there's a round trip time between the server and the client of 100 milliseconds. And so the round trip time is 0.1 second. And let's say we've got an 8 megabit connection, just because it makes the math easy. That's 1 megabyte per second, just dividing by 8. And so the BDP is just you multiply those by each other. You've got 1 megabyte per second, and the amount of time in flight that the data can be flying is 1/10 of a second. So your BDP in this case is 100 kilobytes. So to be able to saturate or to fully utilize the 8 megabit connection with 100 millisecond RTT time, you need to have 100 kilobytes of data in flight all of the time. And that means on the client side, you need to have 100 kilobytes of receive buffer available. And on the send side, you need to have 100 kilobytes of send buffer available. So variations of the BDP that you might actually bump into. So the 400 millisecond, 400 kilobit is sort of the slow 3G, really low-end connection, you've only got a 20 kilobyte in-flight buffer. Sort of ramps up, not too bad. You start getting into the 50 megabit, really fast connection, 25 millisecond round trip time, 1.6 megabytes. When we start getting down to the bottom, it's not unusual for you to have a server architecture where you've got front ends globally, like if you're running a CDN, or even if you've got app servers in multiple regions, that then talk to backends in other regions. And so let's say you've got cloud endpoints in Singapore and in the US, and you've got a 10 gigabit network between them, like an AWS network, for example. You've got a 200 millisecond round trip time between those two servers that need to talk to each other, and a 10 gigabit connection. You've got a 250 megabyte send buffer that you need both on the receive and send side for those servers to be able to actually utilize 10 gigabit connection between them on any single connection. That same server may end up needing to talk to clients that have a 20 kilobyte BDP. So this becomes very much a understand what your server architecture looks like, what servers talk to what other servers in what regions, or what servers talk to clients. The same servers that talk to clients may also need to talk to high-speed servers in other regions, in which case you have to sort of understand what your range of BDPs are that you're sort of looking at to understand sort of what TCP buffer sizes you're looking at. There was a question back there.
So taking into account, just because there's, as you know, there's buffers at every level, and so things like the buffers for raw packet processing, like the ring buffer that are you taking into account those types of buffers as well, and how do you factor that into this, or do you just use kind of TCP at a high level and then?
So the question is, taking in buffers at all sorts of different levels, do those come into account when factoring into this? So ring buffers in the network card, a lot of the on-server stuff ends up being where the buffers live and doing offload, for example, but those still end up being the same TCP send buffer or receive buffer that you've set. It's just where the memory lives as far as the kernel is concerned and how much is actually allocated or not. We will be getting into, there's lots of other buffers, buffer bloat, that does come into play. That's not like server specific, but this is mostly for to saturate those or to fully utilize those different connections. That's the amount of BDP that you have to have available to be in flight at any point in time, regardless of where the buffers live on either end. And so for a given TCP connection, the congestion window, which is how much data the server is going, or either side can have in flight at any given time, ends up largely being the minimum of the receive buffer, the send buffer, and the BDP, or the estimate of the BDP. Because if your receive buffer, remember, both ends need to be able to maintain the same amount of data that's in flight in case they need to retransmit or reorder the data. And so if you have a receive buffer or a send buffer that's like 1K and you need 250 megabytes to fill up your BDP, your TCP connection is only going to be doing 1K at a time because that's all it can retransmit if it happened to lose data in flight. And so you want to sort of make sure that all of your numbers, the browsers, aren't in your control. Most browsers these days tend to use auto-scaling and have fairly large receive windows. When you're talking multiple servers talking to each other, like across regions, then you're in control of both the send and receive buffers. And you want to pay attention. Just realize that you're limited by whatever the smallest is of those numbers. And so a lot of my examples will unfortunately be Linux. If you're running different servers, some of this may or may not be configurable or will be configurable in different ways. So in Linux, you can actually, this is the send buffer, because in most cases when you're talking to a browser, this is what you care about. You can specify a minimum, a default, and a max. And so what those control are, if an application explicitly specifies a send buffer, it will need to fit between the min and the max range. If a browser doesn't specify a send buffer, it will get the default as the initial send buffer. And then most Linux stacks these days will auto-tune the send buffer and grow it up until the max as needed. It usually won't shrink it any, but it'll start at the default and it will grow it as the connection can absorb more and more data. And so, my lovely artistic skills. This is an Nginx server on the right, browser on the left, network pipe in the middle. What you end up with is like the TCP send buffer will absorb all of the data that the server gives it. And so the thing to watch out for is if your send buffers are larger than your BDP, the BDP being what you actually need to fully utilize the connection, you can end up with a situation where the server is writing a whole bunch of data that's not actually going out onto the network yet. And so you end up filling up, and this was actually one of the many problems we had at Cloudflare. Our default TCP send buffers were 5 megabytes. Most web pages and all of their resources are less than 5 megabytes. So we could fill up the entire send buffer with whatever data we got from our backends as quickly as we got data back. And once it's in the send buffer, there is no reordering. It has been sent as far as the server is concerned. And so we would fill up 5 megabytes of data into a pipe, and it would just be sitting there waiting to get delivered however quickly the browser could consume it. And this is sort of one of those legacy leftovers between HTTP 1.1 and moving to HTTP 2, where in an HTTP 1.1 world, each connection only has one request alive on it at a time. You mostly want to be able to shovel data into that connection as quickly and with as little server overhead as possible. And so as large send buffers as you can afford without running out of memory usually gives you some benefits in that case, where you can just dump entire chunks of data and then let the kernel figure it out. When you get into HTTP 2, that's the opposite of what you want. If you want to be able to respond to priority changes quickly, you need to make sure that you have no extra data buffered below the server and between the server and the network. You want whatever next byte of data the server is being sent to actually go out on the network immediately. And so when you have overly large TCP send buffers, you end up with a situation like the first broken example we saw, where all of the, or the Cloudflare example, but where all of the resources largely get delivered in order, but then the high priority resources, even the first one, gets queued behind all of the other requests because everything else is already in the send buffer by the time the high priority request comes in, and it has nowhere to go. There's no way to prioritize it ahead of the other data, even if the server supports prioritization, just because the send buffers are too large. And so, two parts of this. If you're using TCP auto-tuning and you have default buffer sizes that are reasonably small, it will auto-grow to sort of whatever BDP you need, but it'll also at least not start out with an overly large send buffer. So one of our problems or pain points is probably the fact that we had a default of 5 megabytes for a send buffer. You have to be careful. If your application, if you've specified a send buffer, auto-tuning gets disabled. And so like if your web server, you have TCP send buffer explicitly set, it'll disable the auto-tuning and it'll use whatever you've set in the server software. So for the most part, you're best off not setting any explicit TCP send buffer sizes in the web servers. Let auto-tuning do its thing, but then you also have to watch out for what your default and your max is when you're looking at what clients do I talk to and what do they look like and what backends do I talk to, and sort of make sure your maximum buffers can absorb your backend latencies and bandwidth that you need to talk to whatever your backends are. TCP not sent low watt. This is what we actually deployed as the solution. We still have 5 megabyte buffers as far as I know. What TCP not sent low watt does is it gives you can tell it how much overhead beyond BDP to assign the send buffer. And so in our case, we configured it to 16K. And what that says is artificially limit the send buffer to 16K over whatever the current BDP estimate is. And once it dips below that, you can start writing data to it again. And so even if you have a 5 megabyte send buffer, if you've got an actual 20K in-flight BDP with the client at the time, it'll be 36K of data at most that can be in flight at any time. And so we'd have 16K of additional data in the TCP buffer beyond what the client could absorb immediately. And that's very responsive as far as how quickly we can alter priorities, for example. The big benefit of TCP not sent low watt over the TCP auto tuning is it will adjust dynamically lower and higher as a connection over a connection's lifetime as the BDP estimate changes. If you're on like a cell signal or whatever, or as we'll get into a little bit with congestion control, if it overshoots the estimate for the congestion window and then drops back down, TCP not sent low watt will hug that fairly closely and give you probably the best responses on reprioritization. And so what that ends up looking like is the send buffer is basically minimized to the in-flight data only, and it can respond to priority changes as soon as they come in. The other thing to watch out for if you're over buffering the TCP send buffers, or in our case, when we buffered it correctly, a lot of our server metrics went in the wrong direction. Because when we had really large TCP send buffers, the server thought it sent responses completely very quickly because it sent them into the send buffer and it was done with it. And so when we were measuring the time to response complete, for example, the times got significantly longer when the servers all of a sudden were buffering the data and not actually sending it except at the wire speed that the client could consume it. And so it's one of those cases where be careful with the metrics you optimize for. In this case, slower complete response times is actually better end user experience and was a good thing, but it was one of those things that freaked a lot of people out. So congestion control. So up until now, everyone still with me? Everyone's still awake? All right, so up until now, we've been talking about BDP as if the server actually knows what it is. The server has no idea how fast your connection is. And it's like a lot like pushing on a string or guessing in the dark. It throws out data and it checks to see if the data made it, but it has no idea how quickly it can throw out that data. And that's what congestion control is all about, which is trying to probe at and figure out how much data the link can accept and what the actual BDP is without sending too much data. And so what it usually ends up doing is, and this is sort of where TCP slow start comes into play, it starts with an initial congestion window, which in most configurations these days is configured for 10 packets, 15K. And so it sends out 15K of data immediately. And then as, we'll get into the different algorithms, but it increases the amount of data it sends until it detects that the network is full. And then it ramps it down from there. And it just kind of keeps repeating that process to keep probing at, okay, can it absorb more data now? Whoops, no. Okay, can it absorb more data now? Whoops, no. And that ramp up to the network is full is sort of where buffer bloat comes into play. Depending on how the congestion control algorithm determines full. So before BBR, a lot of, so Reno, Cubic, most of the TCP congestion controls were what we call loss-based congestion controls. They throw data at the network until data starts getting lost. I like to sort of think of it as like a Disney park line with those hidden lines back in the network. And if you cram too many people in, they fall off and get eaten by alligators or something. The packets get lost. They're hidden in the network, network buffers, network devices. So like your consumer 5 megabit cable connection, whatever, the head end that throttles that connection down to 5 megabits, maybe receiving data at 100 megabits, has memory inside of it so that it doesn't just throw data away, and it'll accumulate a few megabytes of data sometimes and then trickle it down to the client. And that's what we generally call buffer bloat, which is random network buffers between the client and the server that absorb data silently for you. And so what that ends up being is when it goes to probe to see when it loses data, it can send like 5 megabytes of data before the network throws it away, even if the actual BDP is only like 100 kilobit or kilobytes. If you've ever seen a sawtooth, this is where that congestion control, or this is basically what the congestion window looks like. And this is what a loss-based congestion window looks like. It starts out low with the 10 packet window. It'll increase it. It'll go past the BDP up into buffer bloat. The more buffer bloat you have, the higher it'll go. It'll finally lose a packet after it's gone way above the actual network capacity. And then it drops radically, and it sort of ramps up again from there, and then it drops radically, and it takes fairly wide swings over the actual BDP. And so when we're talking about like the Linux TCP auto-tuning, it will auto-tune itself to whatever the top of that sawtooth is, right? Because that's as big as the buffer gets, and it'll never shrink below that. And so if you have buffer bloat on the wire, and you're using auto-tuning, you're gonna end up with send buffers that are significantly larger than the actual buffers in the wire. BBR, huge fan of BBR, but it's introduced by Google a few years ago at this point, I think. It's just in Linux mainline kernels. You can turn it on. I've got the flags to turn it on. But instead of waiting for a packet to get lost, what BBR does is it watches the pace of acknowledgements, and it keeps increasing the number of packets that it sends on the wire until it sees that it takes longer for the packets to start getting ACKed. And then it goes, hey, you know what? Those packets are probably being buffered. Let me scale back now. And then it probes again and goes, okay, I've got the pace back under control. Let me try being aggressive again. Oh, no, started to take just a little bit longer, and then it ramps it down again. And in no case in this situation does it actually lose packets either. So you don't get into a situation where things have to be retransmitted. And so the sawtooth for a BBR connection ends up looking a lot cleaner. It hugs the actual BDP a lot tighter. I still recommend using TCP not sent low watt, but this would also work much better with the auto-tuning TCP windows because you won't overshoot the actual connection size too much. The main reason for low watt is as the connection profile changes over time, you still want to be able to adjust and go lower. So the real solution at Cloudflare was we turned on both not sent low watt, set that to 16K, and we turned on BBR for pacing. Because either one of those without the other would only be partially effective. You still end up with large buffers either in the network or on the servers. The other thing to watch out for, BBR is sort of evolving, and there's work on a BBR v2 that has less of a problem with this. But when you have multiple TCP connections in contention at the same time, a BBR-paced connection will starve out a packet loss-based connection. And so in the case like we had earlier where you have lots of third parties, for example, and you've got multiple connections contending with each other for bandwidth, if one of those third parties is using BBR and you're not using BBR, they will be getting all of the bandwidth until they've downloaded all of their content, and then your content will start to download. And so when we get to the situation where, and let the network sort it out, the network sorted out isn't as clean as you might hope. It's not like even pacing between the two. Basically, he who uses BBR wins. So if you want your data to take control, that's sort of another knob. For what it's worth, Google and Cloudflare, and I believe Facebook all have BBR turned on. So if you're pulling resources from any of those in connection with, or at the same time as resources from your own origin, you are definitely competing with something that's coming over BBR. The initial congestion window, so I mentioned so the ramp up in sort of probing for where is that sweet spot the first time is TCP slow start. It starts out at the initial congestion window. If you're using old enough servers that used to be 2 to 4 packets, these days 10 is fairly common. A lot of CDNs start off significantly higher than that. 30 is not unusual. It's sort of the starting point where it just guesses and says, okay, I'm just gonna blast out this much data and hope that I'm somewhere under the BDP and then probe up from there. Most congestion control, if it's already over the BDP, will figure it out pretty quickly because increasing by 1 packet will increase the amount of delay and it'll negotiate down. But after that, it goes into what's called TCP slow start. And so what slow start does, I'm gonna peek at my notes just to make sure I get it absolutely right. But it starts with the 10 packets. We'll use 10 as the example. And as each packet is delivered, it increases the congestion window by 1. And so what that effectively does is each round trip, it doubles in size. So the first 10 packets get delivered, you get 10 ACKs, your congestion window grows to 20 packets. So in the second round trip, it delivers 20 packets of data, gets the ACK, and now it's 40 packets. And so it grows exponentially. Unlike the sawtooth side true, instead of a straight line, it's actually a much more exponential growth. But that does also mean, like early on in a TCP connection, if you've got 100K of HTML, your first 15K is probably going to go to your certificate. And then you've got an initial congestion window for actual data delivery that's roughly 30K of data. And then you've got another round trip, and then you're delivering 60K of data. So 90K of data takes 2 round trips in addition to the SSL certificate round trip. We generally look at things in round trips counts because the latency is the killer. So if you're delivering 100K of data, it doesn't just like stream down at 100 kilobit. It's very dependent on what your initial congestion window is and how quickly it ramps up. And odds are you start looking at a couple of round trips. So to figure out the number of round trips you need, to reach the BDP, you can divide the BDP by the initial window. Basically, how many round trip times does it take to get there, and just take the log 2 of that. And so for our BDP estimates we had earlier, going all the way up to the 250 megabyte one, it's honestly not that bad. 19 round trips to get to 250 megabytes, starting at 15K. That's actually pretty good, but it's still 3.8 seconds. And so that's actually the reason, like when you go to do a speed test on any connection, and you go to like speedtest.com or whatever, your connection speed estimate ramps up because it has to warm up the connection and get through these round trips to reach saturation before it can actually estimate what your full utilization is and not be stuck in slow start. But that also, depending on what clients you're talking to, starting out at a number other than 15K, other than 10 packets, might give you some benefit. But you also need to realize getting up to your, so like if you've got your front ends talking to your back ends, are they on persistent connections? Are they constantly opening up new connections? If you're constantly opening up new connections and you've got a 10 gigabit link over 200 milliseconds, if it takes every one of those 3.8 seconds to warm up, you're not helping yourself out, right? And so that's why sort of reuse of connections, keeping them as live as long as possible is really beneficial. You can query what your congestion window is, your initial congestion window, as well as the congestion control algorithm using SS. This one gives the initial congestion window for, in this case, listening connections on a server. And so on my Plex server, just to give that away, the congestion window is 10 and I've got BBR enabled. You can also, so actually configuring the initial congestion window, like I said, it defaults in most modern Linux kernels to 10. Unfortunately, it's not like a syscontrol to set it system-wide. You have to set it on a per route basis and say this specific route has an initial window of 10 or 20 or 30. And so you can configure different initial congestion windows for your outward-facing, your back-end interfaces if you want. Unfortunately, this also makes it a pain in the ass to just like configure a global initial window. The SS you can also use to monitor live congestion windows. It can give you all sorts of stats, like if you're talking to a whole bunch of clients, you can pull what the current congestion window is for all of the clients that are currently connected and start collecting stats to see what is a reasonable window to maybe use for your initial congestion window based on the actual congestion windows calculated over time. The network and the TCP stack aren't the only place there are buffers. There are, like you said earlier, there are buffers everywhere, and they all suck. So we talked about the TCP buffers. There are also buffers in the SSL TLS layer where it does the framing for the TLS frames. The HTTP2 implementation inside of the server itself has its own buffers. The upstream read buffers within the server for the backend connections have its own either file read buffers or HTTP and TCP buffers on the read side. If you don't have enough data available to prioritize because you have too small upstream buffers, you end up in a situation that looks a lot like Cloudflare's, where you've got data round robining between a bunch of different requests because there wasn't enough upstream data available to fill the downstream buffer at a given time. And so you kind of want your right side buffers to be big and your left side buffers to be as small as possible while still saturating the connection. And it's kind of a balance to play with as far as tuning all of that. You also want to watch out. Odds are your servers are not used to the model that HTTP2 changes, where your front end, the termination point can get 100 simultaneous requests all at the same time. And all of those turn into 100 backend requests all happening at the same time. But the lowest priority of those 100 backend requests might delay for like 30 seconds before it starts streaming to the client. And so if you've got server write timeouts, for example, on your backends that are talking to your HTTP2 termination point, you could end up in a situation where you're timing out in HTTP2 where you weren't in HTTP1, because in HTTP1 it would basically just shuffle the data through as quickly as it could. And so you've got cases where your servers are going to have long delays in things that it's talking to. And that's a very real problem that someone had on Twitter not a month ago, I think. When they switched over to HTTP2, they started breaking their application servers because they were exceeding their timeouts that they were expecting now. Yes, back and back.
Is there any situations that you mentioned you rely on auto-tune, or that you generally want to rely on auto-tune a lot? Is there any situations from your personal experience where you don't rely on auto-tune and you want to make things more deterministic?
So I recommended using auto-tune, but are there situations where you shouldn't use auto-tune and you want it more deterministic? So auto-tune doesn't really come into play in at least Cloudflare's deployment because we're using low watt. And so low watt makes it somewhat more deterministic in that, I guess it makes it more undeterministic because it's another thing that varies. If you've got a server that's got a consistent mix of clients that you can predict what buffer sizes you need, then maybe turning off auto-tuning is worthwhile. I can't think of any good reasons why you'd want to, though. Odds are you're better off leaving auto-tune on and just setting your default and your max to be within a window where you want to keep it, just so that you can avoid over-allocating for clients that don't need large buffers, but still grow the buffers to those clients that do without having to over-allocate for every client and rely on low watt to keep the actual writes in control. Hopefully that answered. Yeah, so in this case, like the last request in the waterfall in this test was 10 seconds before it started actually streaming the data down to the client after it had received it from the backend server. And so if the backend server behind the HTTP server has less than a 10-second write delay, for example, because it's not used to talking in this case, you're going to start to see problems. As far as the actual servers go, H2O is sort of the gold standard for HTTP2 implementations. It was built explicitly to support HTTP2 and does an extremely good job with prioritization and everything else right out of the box. Apache also looks like it does really good prioritization. Nginx, yeah, no, not so much. I've got a ticket I filed. The dev team is still in denial that there's actually a problem, so we're waiting for them to get into acceptance. But yeah, so Nginx's problem is their HTTP2 box in particular does know how to do prioritization. Unfortunately, the way it reads from the upstream buffers, it doesn't refill read buffers as it's going, so it'll kind of it'll pull from the highest priority upstream buffer that it knows it has until that buffer's empty, and then it'll go on to the next request, even if that buffer actually could read more data in. And so the way it reads from the upstream buffers and the way it handles the downstream buffers, it ends up creating, let's see if I've got, so it ends up creating waterfalls with split data delivery, where instead of delivering all of the highest priority requests at a time, you get little shards of it interleaved with other requests all at the same time. And this is unfortunately where you're in the, not a lot you can do other than beg or switch servers, but usually it's easier to try and file bugs with the server implementation or put something in front of it that speaks the protocol. So is TLS fast yet? Ilya Grigorik from Google has an awesome high-performance browser networking book. This is sort of the TLS high points from it. So for HTTP2 to work performantly, you need TLS to perform well, because HTTP2 is all over TLS. And so a couple of things to watch out for. OCSP, certificate verification checks, for example. Depending on the browser, so all browsers, when they do an OCSP verification check to make sure the certificate hasn't been revoked, will stop right in the middle of the TLS negotiation, go out to the verification server, verify the certificate, and then continue with the TLS negotiation. And that usually ends up with 3 extra round trips. You're doing a DNS, socket connect, and request for the verification check, all while you're in the middle of trying to do a critical TLS negotiation to download the HTML. And so adding 3 more round trips to your what would have hopefully have been 3 round trip TLS negotiation is extremely painful. Sometimes if you've got a long enough certificate chain, it'll do multiples of those sequentially, because it needs to verify the leaf certificate and then the intermediate certificate before it gets to the trust root that it knows about. So usually if you see gaps in the TLS negotiation with some OCSP verification right above it, it's because it's doing cert verification checks. And it's completely useless, because if the cert verification just doesn't happen or doesn't work for whatever reason, the browser goes, oh, well, it must be good. So it throws it out anyway. So it doesn't actually provide any value. Firefox will verify every certificate regardless. Chrome will only verify EV certificates. So if you can get by with domain verification instead of the EV green chip in the address bar, you will avoid having to ever do a cert verification check in Chrome, and it's a huge performance win. Luckily, most mobile browsers don't show any EV indicators, so there's a lot less carrots for the sellers of EV certificates, or for the marketing teams that insist, no, we must have our company name in the address bar in the certificate. So if you can try and push towards DV certs, you'll get much better performance. You can, yeah, so there will be, oh yeah, in the certificate there has. The other thing to do is OCSP stapling. Your server, instead of requiring the browser to go out and do the verification check, your server can pre-verify the certificate and put an authenticated verification stapled inside of the TLS negotiation. It only works for one step in the chain, so if you've got a really long certificate chain, you'll still end up doing some, but it can help get rid of a lot of the OCSP verification overhead. You can verify it using OpenSSL or SSL Labs check will tell you if your certificates are being stapled or not. You also have to watch out for, so we talked about the round trips for initial congestion window, 10 packet, 15K initial size. So OCSP stapling increases the size of the certificate. If you've got a big enough certificate, you may exceed the 15K initial congestion window and end up with having to do 2 round trips for the certificate to deliver the certificate to the browser. So you have to watch out for how many round trips does it take to actually do the TLS negotiation, and it should be 1. You should never have to do more than 1 round trip as part of the TLS handshake. And it's not uncommon to see 2 or 3 round trips. One of the big reasons is large certificates. Nginx and HA proxy also have bugs in earlier versions where they, for whatever reason, they have their own logic that requires extra round trips in the TLS negotiation. Probably don't need to worry about the details of how TLS false start works, but knowing if you're doing HTTP2, you've already got ALPN because it's advertising HTTP2. That's the only way to do HTTP2. And I'm pretty sure you can't do TLS without a forward security cipher suite anymore. So pretty much the requirements to get false start for TLS to get you all the way down to 1 round trip handshake, if you're doing HTTP2, should hopefully already be in place. Yeah, so probably just between stapling and false start for doing HTTP2, everything else should largely be taken care of for you automatically. And so in this case, we still ended up with the situation where it was 2 round trips. And the first byte time. So I usually end up using the orange part of this bar is the socket connect time, which usually ends up being a good proxy for what's the round trip time between the browser and the server. And so that gives you a good estimate for how wide the bars should be for the pink and for the green, for the TLS negotiation and for the first byte delivery. And this is when we talked about TLS buffers. TLS has its own window sizing, and if the TLS windows aren't dynamic, you can end up with a situation where it will try to buffer up to 16K even if 16K isn't available, and it'll wait for a timeout before it sends a padded buffer. So you need to be able to support TLS dynamic record sizing, where it will actually send a TLS record the size of the available data that you have in flight. I know newer versions of Nginx will do it. Older versions did not. Most CDNs will, but that's definitely is TLSfastjet.com has a table showing what the deployment status looks like for TLS record sizes. Yeah, so this is a little out of date, although most servers still don't optimize for that case. And so, yep, it works. So if you really like this stuff, it doesn't include any of the HTTP2 stuff I've gone into yet, but Ilya's got an awesome browser home, and it's free. If you go to hpbn.co online, high performance browser networking, which gets into sort of all of the details for how browsers work and how TLS works to optimize the connections. So at the end of all of this, so what do you actually do to get your deployment fixed? Well, use one of the 4 or 9, I guess, CDNs that work, and you can call it a day. If you're on one of those, not a problem. Otherwise, set reasonable default TCP send buffer sizes, hopefully with auto tuning. Enable not sent low watt, enable BBR. That should hopefully give you fairly responsive HTTP2 prioritization, assuming you also have a server that actually supports prioritization. Hopefully at that point, your waterfalls will look somewhat close to the optimal case and not like one of the completely confusing broken cases. On Linux, what that ends up looking like, so this case, definitely don't use copy and paste these numbers. These are for the 250 megabyte upper sized. You will probably melt your production servers if you just paste these numbers in. But this has like a 100K default buffer size, a 250 meg maximum buffer size. Turns on window scaling so you can actually have large buffers, turns on not sent low watt, and the last two lines are what's needed to turn on BBR. Although soon FQ will not be needed to turn on BBR. FQ does fair queuing and pacing at the TCP level, but it's currently required for BBR to actually work when you deploy. So are we okay? Everyone's still with me? Yes.
After tuning the buffers for HTTP2, have you seen any side effects on HTTP1, either for the good or for the bad?
Have we seen any side effects on HTTP1 after tuning the buffers for HTTP2? No. We saw no degradation in the HTTP1 traffic. We also did not see any increase in our CPU utilization. That was the main thing we were concerned about. Because when we set the low watt to 16K, we only have 16K of buffer available for the main loop to be able to, or the event loop to be able to read more data and fill it in before the buffer drops down below the actual BDP. And we were afraid we'd be spinning the main loop really hard and increasing the CPU utilization, but it was, if there was any, it didn't show up on any of our graphs. So it was much less than like a 1% tick in anything. But the HTTP1 throughput, we saw no negative impact on anything. And we monitored that stuff really closely. So other landmines to watch out for. HTTP2 push. Don't. Stay away from it. It's great on paper. And so what HTTP2 push lets you do is the HTTP2 server can send down resources that the browser hasn't asked for. So let's say the server gets a request for HTML, and the server knows, okay, you're also going to need this JavaScript and this CSS file. I'll push those down to you even though you haven't asked for them yet. And by the way, here's your HTML. A lot of servers can also be configured and are by default to automatically trigger push based on seeing link rel equals preload headers in responses. Unfortunately, people have like really abused preload, so you end up seeing cases where servers are pushing 20 different resources, some of which may or may not be in cache. But the big issue with HTTP2 push is it doesn't actually make anything faster in the vast majority of cases. The only case anyone's been able to show performance benefit in HTTP2 push is if you've got a slow HTML, like you know your backends are going to take 3 seconds to respond or whatever, and you know exactly what your BDP is and how much data you can push to fill that 3 seconds of dead time, and you can push just that amount of data in before the HTML comes in, you can get a gain. But if you can't get it exactly right, you end up competing with the HTML. And so the resources that you're pushing down are slowing down the actual delivery of the HTML or other things that the browser's asked for. And so in 99.9% of cases, HTTP2 push is actually making pages slower. Browsers also hate it because it's a pain in the ass to implement on the browser side, so I wouldn't be surprised to see support for it go away at some point. I know Chrome certainly made noise about it, but if you have it deployed, and unfortunately Cloudflare has it deployed as well, consider turning it off or at least measuring what the impact is to see if there really are any gains from having it enabled. Yeah, so that's pretty much everything I just talked about. Preloading. So we talked a little bit about what can you do for fonts to tell the browser, hey, you really want to load this. And so adding link rel equals preload to the document, you can tell it to preload any resource ahead of time and say, hey, you're going to need this. Unfortunately, that's not free. So whatever you're preloading is competing with the resources the browser would normally be loading or needing. And so in the case of preloading fonts, you're actually competing with the render blocking JavaScript. And so whatever bandwidth time it takes to download the fonts, it delays the render of the entire page by that because you've all of a sudden said, hey, these fonts are really important, download them really early. And so it ends up blocking all render instead of just blocking the text render. Again, that may be something you want to do. Just be really aware that nothing comes for free. There's also Chrome bugs, well, idiosyncrasies. Because of Chrome's implementation of app cache, preload resources, no matter where you define them in the document, end up loading before anything the parser actually discovers. Because preloads get kicked off basically at the network level, Chrome has some overhead in starting the parser because it needs to check with the app cache and make sure it doesn't need to do an offline anything with it. And so in the time it takes to do that before the parser, the main parser has started and can start fetching anything, the preloads can start getting initiated. And so even if you put a preload hint like at the end of the document saying, you know, I want you to load this, but maybe don't load it before anything else in the top of the document, it doesn't matter. It's going to be one of the first things that the browser issues, and it's going to compete with the other critical resources. So no matter what you try to do, if you're preloading, it's going to get a really high priority and be issued really soon. And this one was a fun one. So Andy Davies, we talked about it a little earlier. One of the customer sites he was working with was preloading a video. You can imagine how that went. So it's downloading an entire huge video while it's trying to load the critical CSS and styles and everything else. It's one of those cases where you give developers a little bit of control and they go wild and preload everything. It'll make everything faster. When everything's faster, nothing is, right? Resource unbundling. So one of the hopes, I guess you'd say, for when HTTP 2 rolled out was, since it's cheaper to issue a whole bunch of requests, we could stop bundling our JS and start, because we used to combine all our JavaScript into one file and all our CSS into one file and sprite our images and things like that. And one of the hopes was with, okay, HTTP 2, it's now much cheaper, it's all over one connection, we can deliver all these things concurrently. Let's stop doing that and we can deliver all of the JavaScript files separately. We can deliver all of the images as needed. Unfortunately, the real world introduced itself. And so like with the JavaScript files, when you break them up, you no longer have a shared dictionary across them. So they don't compress as well. Each one compresses separately. So you get much less compression. And it turns out the browsers, Chrome in particular, does not deal well with lots of small requests. Each one of those is a round trip between different processes, causing IPCs and context switches. But it's also a disk cache check to see, hey, is this resource in the cache? And those can be really expensive. And so, especially if you've got like ad blockers and AV that gets in the way of all of the requests. And so if you take like what used to be one request and now it's 100 separate requests, it ends up being really slow. And so the Khan Academy actually tried this because I guess they drank the Kool-Aid and said, hey, we'll unbundle everything. And they had like 200 JavaScript files that they were loading. And it got orders of magnitude slower. And so they have an awesome blog post about it. So prioritization, I mentioned a little bit that Cloudflare rolled out server-side prioritization. The browser asks for things in a certain order. Doesn't mean you really have to do what it asks for. I mean, getting it completely wrong is bad, but if you think you can do better than what the browsers are asking for, it's certainly an area for innovation and for experimenting. We looked at how the different browsers have completely different schemes. If you're supporting Edge and IE, for example, you can certainly do a whole lot better than what Edge and IE are asking for. But if your application knows better than even what Chrome or what the other browsers are asking for, you're welcome to implement something else. If you use Cloudflare, you can program it with workers, but also if you're rolling your own HTTP 2 implementations or sort of experimenting with optimization areas, that's an area that's certainly very ripe for optimization. There's nothing stopping you for rolling out your own scheme independent of what the browsers do. Quick. HTTP 3 will fix everything, right? So Quick, or HTTP 3, which is on top of Quick, it's UDP based, runs over port 443. It basically moves all of the TCP logic, the congestion control, the retransmits, the bandwidth estimation, all of that kind of stuff up into the application layer and runs it over UDP. And so there's much less failure modes around OS configuration. You don't have to worry about configuring BBR and send buffers and all of that kind of stuff because it's all implemented. It includes a BBR implementation by default, I think, most stacks. But it also does mean all of that responsibility is now in the application. So you're trusting your server's internal TCP implementation, if you would. So Nginx's quick implementation is going to be their own congestion control and everything else. So you've got a lot more trust in your software provider there. It also moves loss recovery. So whenever a packet is lost in H2, the entire stream, or the entire connection stalls until that one packet can get retransmitted. With Quick, it moves it to a per stream level. So when one packet gets lost, only that one stream within the virtual Quick stream stalls. Any other streams that are going on concurrently can continue because they don't have out of order dependencies on that one packet that was lost. So it brings back a little bit of the, so there was a little bit of a performance hit moving from HTTP1 across multiple connections to HTTP2 on a single connection because of that stalling the whole connection and all requests on it. And this is basically Quick's big win over HTTP2 is it brings it back to where you can actually make a lot of forward progress even if you lose one packet in the middle. The last bullet is sort of a thing to be very aware of is HTTP3 will never replace HTTP2. It is UDP over 443. That is never going to be fully available everywhere on the internet. Treat it as a progressive enhancement. The reason I expect you're actually going to see penetration levels drop for HTTP3 rather than increase is HTTP3 also includes encrypted SNI. So SNI is when you're doing the certificate negotiation with the server, the client says, hey, I want to talk to www.example.com in the clear. So network devices in the middle can see, hey, what domains are you browsing even though you're browsing encrypted? And so TLS 1.3 and HTTP3 encrypts that information as part of the TLS handshake, so network devices in the middle can't see the servers you're talking to. Turns out, network devices in the middle really want to see what servers you're talking to. In Britain, they're legally required to filter porn and things like that. And so the easiest way to do that is block UDP 443 at the network level, and all of a sudden you have visibility into all the connections going through your networks again. Same thing goes for corporate proxies, where they like to man in the middle all of your traffic and inspect all of your browsing. They'll also be blocking Quick. So expect to see penetration drop as more and more man-in-the-middle people need to inspect traffic for good or for bad. HTTP3 prioritization. Currently, the efforts are around replicating what HTTP2 does with the tree. There is a offshoot where we're trying to come up with something better that's a little easier to rationalize, so we don't have this massive tree structure that we're trying to figure out how to balance and deliver things optimally. There is a HTTP working group where most of the discussions are going on if you wanted to join. But that is it. So thank you, and questions. Everyone is asleep or ready to go. Awesome. All right, well, thank you so much. You guys have been awesome.